All right, it's the next morning. I have new energy and hope and kind of think that we get this thing finished today. I recorded yesterday for, I think, about 8 hours in total, maybe a bit less. I have no idea how long it's going to be today. I think we made pretty good progress yesterday, but there's still a couple of things missing. The last thing that we did yesterday was the attention block. So if we go back to our architecture diagram, we have basically this block done, except for the residual connection. We need to finish that. And after that, we have our MLP block. So the layer normalization, MLP, and another residual. So let's first do the residual connection. And that should be pretty simple. All we need really is a for loop across all the elements of our one matrix and all the elements of the other matrix. And we need to sum those together into an output matrix. So I'm just going to create a pointer in one. And this is going to be our output. Or actually, let's make in one the input to the attention block. So this is our embedding layer index. So it should be the embedding out. And actually, let's make a second pointer right here and call it layer in, which for now is just going to be this right here. But as we have more layers, we will actually make this something else. So this will be some kind of if conditional that's if the layer index is 0, we're going to take the output of the embedding layer. And if it's something else, it's going to be the output of the second residual connection of the last layer. Okay, so this is going to be layer in. And I think we don't have any other use. Embedding out. Yep, looks good. All right, so back to our residual. We now can use our layer in as our first input right here. And our second pointer is going to be the output of the last attention projection, so C projection, which is activations, our layer, attention block, and C projection out. And we need an output, which we actually should create. So let's go to activations, go to the struct, and in here, let's just create another struct and call that res2, sorry, res1, our first residual connection. And the dimension of this output is going to be the same as our two inputs, which are dsequence times demodel. All right. So we can just use this right here. Activations, again, our layer, and res1 dot out. And now all we have to do is to loop through all the elements. So I'm just going to make another variable called, actually, let's make these two const. Create another variable that's going to be out plus the number of elements in our matrix, which is, again, some input size, because we don't want to add the entire two matrices, but only up to our actual input length. So we have input size times demodel. And now we can just create a simple for loop that checks if out has reached out end, and otherwise just increments in one, in two, and out. And now we just write to out the result of adding in one plus in two. And this is our residual layer. So now instead of checking the projection out right here, let's check the output of our first residual connection against our Python implementation. The rest should be fine. And it's 358. So let's go to Python. And instead of printing here, let's print right here. Press one out. 358. I actually forgot our result. 358. All right, cool. So the residual connection works as it does in Python. So now we actually have our complete first block done. And I think I said this yesterday, but this was actually probably the most difficult part of this entire network. We can see this in our Python implementation, that one of the most, the smaller, uh, the attention block is really where most of the complicated things are going on. And the MLP block is just a linear layer, like uh, sorry, we are down here. It's a layer normalization. And then one linear projection, a Gaussian operation on all of the elements, and then a projection back into our model dimension. So let's implement that. We need a second activation or another activation struct right here, which is just going to be the same as our first layer normalization. It's going to be ln2 with the same dimensions. And we are just going to, we could actually copy the code that we had right here for our first layer normalization. But it is probably better to factor this out into its own function. So let's just take all of this. Yeah, like this. And factor it out into its own function. And we're going to do basically the same thing that we did for our fully connected layer, where we just create a function ln, and it's going to take a struct as its input, which makes it a bit easier on the call side, where we can then just say struct member equals our input, and we have the name of the function parameter written out. And let's copy our code in here, and let's think what we need in our struct. It's going to be pretty much the same as our fully connected layer. So let's just copy that, where we have an input, which is input size times model dimension. We have a weight array, which is the model long, same for the bias. We have an output matrix. And now we don't have in and out count. We just have, because they're the same. So let's just keep in count. And we have sample count, which is the number of elements in our sequence. And now we can do the same thing that we did for our fully connected layer, where we just rename these members of the function. This is going to be sample count. The model is going to be our ln in count. And actually call this layer in. Oh, no, okay. Sorry. It totally makes sense. was confused why it was called layer in, but we actually just create the pointer. Okay, we have our input, and then in end is going to be in plus an in count. That's just the number of elements per row. In reset is going to stay in. And we're going to divide by ln in count as well. We're just doing a mean operation. The same should be done for this, where we divide by ln in count. This is our reciprocal standard deviation. Weight is now just going to be ln weight, and same for the bias. Our output matrix is very simply ln out. And again, we use the in count as the dimension per row. Okay, and I think that's all we needed to do. I think this looks good. And let's try to replace our layer normalization that we had right here with a call to our layer normalization function. So we have struct ln, and it's going to have the same members as this one, except it has only in count. And in is just going to be our layer in pointer. The weight is going to be ln1.weight. Same here for the bias. And our output is going to be ln1.out. We use right here, ln1.out. In count is demodel, that's correct. Sample count is input size, that's also correct. So let's try if we still get the same result at the end of our residual connection. And we have a couple of errors. Let's go to this one first. Yeah, that's actually a good warning. Again, we need to make these two, or these three actually const. And I guess the same is true for weights and biases. All right, and we get the same result as we did before. Okay, and now we can add our, let me just go back to the architecture. We can go back to this block and our second layer normalization. For now, I'm just going to keep this right here. And I'm just going to copy the call to the layer normalization from up here. Okay. This time our input is going to be the result of our first residual connection. So that's our activations, struct. Again, we select the correct layer. We get res1 out. The weight is going to be ln2 weight, and same for the bias. And the output is going to be in ln2 out, and we actually need to create this. Oh, actually, we did. Cool. Oh, no, we didn't. This is the parameters. Oh, no, we actually did. Okay. ln2 out. And our in count, like the dimension of each row, is demodel again. That's correct. And our input size as the sample count. And let's copy over this testing code. Let's check if the result of our layer normalization is actually what we would expect. So ln2 out, and we get 280. So let's go to Python. And let's take these statements and put them right here. This is going to be ln2 out to 180. Yep, same value. All right, so our second layer normalization seems to work. Let's comment this out again. And let's go to the next one, which is our MLP block. And if we go if we go back to our architecture drawing, the MLP block is these two transformations, one from the demodel space into 4 times demodel, then our gallery operation, and then a transformation back from the 4 times demodel into the demodel dimension. So this should be relatively simple. We're just going to reuse our FC function call that we have in the attention block for this block as well. So our input to this is going to be the output of ln2. Our weights are going to be, do all of these at the same time. CFC, I think, was the name of the transform matrix, and it was in the MLP struct. Let's make sure this exists. Yep. Weight Bison out. And let's actually create this output. So we have our, again, this is just going to be the same struct that we have right here, where we start with a struct MLP, and it will contain 3 structs within it that are just called like the transform matrices that we use. So this is going to be CFC out, and its dimension is going to be, again, we have sequence number of rows and 4 times demodel as our, as our output dimension. Then we have a second struct, which is going to be the output of our value operation, which keeps the same dimensionality. And then we have a final struct like this. That is the output of our C projection transform. And this is just going to be demodel dimensions. Okay, and let's go back here. In count is going to be demodel, and the out count is going to be 4 times demodel. And I think that should be it. Let's copy over our testing code again. And I think we can actually just delete these. All right. And let's print the sum of all the members of the matrix. So this is mlp.cfc out. And it's input size times 4 times the model. And we get about 235,000. Let's check if this is correct. This is going to be this value. 235,000, and we had, I think, yep, the same value roughly in C as well. So this looks good. And the next thing we need to do is to do our value operation. So if we go back, I think I actually didn't write down what the value operation is, but I think I mentioned it. So the value operation, actually we can just look at Chrome. The Gauge operation is x multiplied by the CDF of the standard normal distribution. So CDF, I think I mentioned this yesterday, is the area under the curve of this function. And doing an integral numerically isn't really a good idea. So we use a C standard library function, which is called the error function. And basically the error function and the standard normal distribution are, or the CDF of the standard normal distribution are very tightly related. So we just have to take this result of the error function and kind of move and scale it a bit to get the area under the curve of the standard normal distribution. So this function is going to be important again when we do the backward pass, where we have to actually find the derivative of this function. But for now, let's just take this equation and implement it just one-to-one in our C code. And this is going to be like this x value is going to be a single element of our matrix. So we do the same operation for each element in the matrix. So just as we did for our residual connection, actually let's put this in a block so we don't use the variable names in the top scope. Let's just copy this. And now we just have one input, so we can delete this line, and this is going to be simply in. And it's going to be the output of our CFC transformation. And the output of this is going to be mlp.value out. And we have input size times 4 times the model elements in this matrix. And again, we simply iterate over all the values. And in here, we're going to first compute the CDF, which is going to be this 1/2 times 1 plus error function of this value. So the value of the CDF is 0.5 times 1 plus the error function. And we're going to want the float version of this function. Of our input divided by the square root of 2. And if I remember correctly, we actually have a constant for that. We do, and we need to convert this to a float because the constant is a double. In divided by the square root of 2. Actually, it would be kind of nice if we didn't have to do the division. Yeah, so there's a square root of 1 divided by 2 as well. So let's use that instead. Square root of 1 divided by 2. All right. And we multiply by that. And now we just have to multiply our input value times the value of the CDF for our given x. And this should be our implementation of the value function. So let's check. Oh, by the way, one note on this. This is not normally how the value function is implemented, because calling this error function is actually quite expensive. And you normally use an approximation of this function. At least this is what I've I've read in other places. I'm actually not like I haven't tried it myself of using this over the approximation of this function is actually slower. Um, but just as a side note, you might see slightly different implementations of this function, which are going to be approximations. I mean, this is of course also just an approximation because we are in code after all. And let's try to print the result of that. And again, same dimensionality as our input. And we get roughly minus 10,000. And let's try to check what we get in Python. And we use the MLP value out. And this is minus 10,345. And what do we get in C? 10,345. Awesome. Yeah, all right. One thing I'm seeing is that we are getting slower in our execution. So one thing I'm going to do for now is to go into our build script and just enable optimizations. So I'm going to use O2 optimizations for now. And it seems that we are a bit faster now. Of course, the compilation will take a bit longer, but I think this is being offset by faster execution speed. So now we are almost done with the MLP block as well. The last two things we need to do are the transform back from the 4 times model dimensional space into our model dimensional space. And then the final residual connection with the input to the MLP block with the result of this transform back. Okay, let's just copy our previous call to our fully connected function. And this time our output is going to be the output of the value function. So mlp.value. The weight is going to be C projection, and same for these three. This time our input is going to be 4 times dmodel, and our output dimensionality is going to be dmodel. And this should be it. So now let's check the result for this as well. Minus 514. And in Python, we get the same result. Awesome. So now for the very last step, and we're just going to, I think it's easiest to just copy this over because we only have two places where we do a residual connection. So I don't think we need to factor this out into its own function. This time our input is going to be the output of our previous residual connection. And actually we have this way to do that, res1.out. And our second input is going to be the output of our MLP C projection. And this time the output is going to be res2 out. Res2 out. And again, we have our same dimensionality as always. And let's try to print, oops, the result of that. Res2 out. And this time it's a smaller matrix. and we get minus 155. Let's check this with our Python implementation. Rest2 out 155, minus 155. Same result. Awesome. So just like that, we have finished the main parts of our transformer implementation. If you go back to the diagram, we now have this embedding part, and we have one completed layer. So now the next step, before we do the final layer normalization, is to have a for loop over all the layers in our model and take the result of the previous layer and give it to the input of the next layer. So let's try to implement that. And this is just going to start with a for loop, which is going to replace our layer index variable that we have down here. So we have 12 layers, and we just increment that. Let's go down here and put the closing brace, indent all of this. And now we have to do the same thing that we did in Python, where we have a conditional for the input to this layer. So for the first layer, this is going to be the output of our embedding. And for all the other layers, it's going to be the output of layer I minus 1, so the previous layer, and we want its residual output of the second residual connection. And this is going to be the input to the layer normalization. Actually, let's delete this. And it should also be the input to our first residual connection. That looks good as well. And now let's check if the output of our very last layer's second residual connection, so the very last output of the last layer, which is going to be the input of our final layer normalization, if that is the same as what we would expect in Python. So in Python, we're just going to do if layer I is equal to 11, so the last layer, then we want to print the output of the second residual connection. And this we can then check in C if we get the same result. So here we get minus 3858. And let's see what we get in C. So layer 11, and it's going to be the output of the second residual connection. That looks correct. And we get, first try, roughly the same result that we get in Python. So pretty happy with that, which means we have fully completed the forward pass of the vast majority of our model. So the very last thing is a final layer normalization, and then a final linear layer where we use our embedding matrix to get our final output vector. All right, let's do the layer normalization first. And again, I'm just going to copy over the code that we used for all the other layer normalizations. Okay. This time our input is going to be, oops, the 11th layer and the output of the second residual connection. The weight is going to be lnf dot weight, bias, and out. And let's create our, does this not exist? Oh yeah, layer I. Okay. Yeah, makes sense. H11, and this doesn't exist. By the way, I'm just seeing, despite having errors during compilation, we still execute our program, the last program that we executed. So I think this is set minus E to do this. Set minus E just causes the script to cancel its execution when one of the commands exits with a non-zero error code. That's exactly what we want. And now let's go back to our activations and create an output for our final layer normalization. Call this lnf. Again, we have dsequence times dmodel values in this matrix. And let's also print the result of that. lnf.out. And we have roughly 16,000. 16654. Let's do the same thing in Python. Delete this. lnf out. 16653. This is very similar to what we get in our code. Awesome. Okay, one more thing to go. So we can probably just use our fc function call to do the final transform. So if you remember in Python, we just used a linear layer, although I think we actually can't do that because actually we might. Uh, in Python, we had to transpose our weights, and we didn't do that for the very last one. But I think that's because the weight matrix is transposed in the first place. So let's try to think through this. Go back to the dimensionality. So for all of our other uh, FC function calls, we had matrices that had the input dimension as the number of rows and the output dimension as the number of columns. So in this case, we have 50,000, which is our output dimension, as the number of rows, and 768, which is our input dimension, as the number of columns. So we actually won't be able to use our FC function call directly to calculate the result of our unembedding transform. So we have to write this logic ourselves. Shouldn't be too hard. Let's create a for loop that first loops through all our input rows. And now what are we going to do for the matrix multiplication. So again, we remember we have 50,000 rows and model many columns. And now for normal matrix multiplication, you would have a matrix that has model as its number of rows, because the number of columns in the first matrix and the number of rows in the second one must match. And this is going to be the input size. Except in our case, this is slightly different because in our implementation, all the inputs are sequentially after one another as rows. So this matrix is actually transposed in our code. But let's still go uh, through this matrix multiplication where we take each row of the transform matrix, multiply it by one column for transformed matrix, to get one element in the output matrix. And we just repeat this for all the rows in the transform matrix with the same vector in our input matrix to get all the elements of this output vector. So doing this in our code is actually pretty simple because we just have to take one row of our input matrix. Again, we are transposed, and multiply that by all the rows of our embedding matrix. And this is how we get one output row of the final output matrix. And the output matrix has, I should have drawn this a bit longer because this is the vocab dimensionality. So one vector in our input is being multiplied by 50,000 vectors from our transform matrix to get one element of the output vector each. All right, let's try to implement that. And I think we should start by creating an output for this. So activations, and I'm just going to call this unembedding out. I think this is how we call it in Python. Yep. So float out. And the size of this is going to be input input many rows. So up to the sequence. And each row will have vocab many columns. Okay. So let's start creating our pointers here. Our input is just going to be one row of the last output matrix, which in our case is activations lnf dot out. And we want the ith row, depending on our sequence item that we are calculating the output for, I times the model. Then we have our weight pointer, which is just parameters. I think I created this in the wrong spot, actually. Yeah, this should be in the activations. And our matrix is just our WT matrix, the weight matrix. And we have an output, which is going to be the activations unembedding dot out. And again, we need to offset that by I times the number of elements per row, which in this case is the vocab. And now we can do a very similar thing to what we did in our FC function, where we have a wait end and actually in this case it's going to be a bit different. Because in our FC function, we created the output, not element by element, but instead we created one vector, then another vector and added that, then another vector and added that, until we go through all of the rows in our weight matrix. But this time, since our transform matrix is transposed, we're going to do it a bit differently. And as I explained just now, uh, produce one output item at a time. Basically, it's just a dot product of this vector and this vector, and then a dot product of this, and then the third and this to get one element each. So I'll just have a temporary variable uh, dot initialized to 0. And let's create the main loop for this. So dot is going to be our input vector, one element of that, or the current element rather, in times one element of our transform matrix, in times weight. We have to increment in by 1, and we have to increment our weight pointer by 1. And then we need to make sure that we notice when we have gone through one entire row of our transform matrix or one iteration of our input column. So I'm just going to create a in end. Actually, this can be a const in end. And this is just going to be a in plus the model. So until we've reached the end of this row, again, we are transposed. And I'll make a temporary like a reset value for in. So you can detect if in is equal to in end. And if that's the case, we're going to reset in to its original value. So we can start processing this matrix again. But we're not resetting our model pointer because we do actually want to progress to the next row of this matrix. But what we need to do is we need to set our current out pointer to the value of the dot product, then reset our dot product back to 0, and then increment our out pointer. And this is how we go through the model, so through the weight matrix, row by row, and through our output matrix, element by element, each element being the dot product. Okay, let's make sure that this is correct, but I think it looks good. All right, now we need to check if we have reached the end of our weight matrix. So I'm also creating, this is also const, by the way. Same for this. we need a weight, and this is just weight plus d vocab times d model. This is the number of elements in our weight matrix. And here we just check if weight is equal to weight end. And if that's the case, we break from our loop. All right, I think that was basically it already. And let's check if we get the same result as we do in Python. I'm a bit worried maybe if I think it should be fine. I was worried that we have a lot of elements in our output matrix, and we might get into issues with numerical stability because we have one accumulator where we just add all the values, and the values might be very small, and our accumulator might be very large. So we might lose precision along the way. But let's just see how this goes. So this is input size times the vocab. That's our output dimension. And our output matrix is unembedding dot out. And let's see what our total is. Dot is actually not a pointer. Yep. Yeah, this seems like we might be getting into issues. Um, let's still just see what we get in Python. I mean, here we're using a double, but in Python we might be kind of hard to tell. Maybe Torch just like a row or column sum first and then sums up those values. Let's just print the value. So this is unembedding out. And oh yeah, we need to delete this. Okay, actually, it does seem kind of okay. Minus 3.538. Let's just copy this. Let's print our value in C again. Okay, let's 1, 2, 3, 4, 5, 6, 7, 8. All right, it looks like we're actually pretty much spot on. So now let's do one last thing, which we also did in Python, which is to take the maximum value, or rather the index of the maximum value of the last row of our unembedding output. And the index of this maximum element is going to be the token that has the highest probability of being the next one in the sequence. And if we just decode that again, as we do in Python, into a string, we should hopefully be getting the string that we get in Python as well. So this is just going to be a simple for loop through all the vocab elements of this row. And we need to keep track of the maximum value, which I'm going to initialize to minus infinity. And then the index of this element, just initialized to 0. Doesn't actually matter. So if this may just create a pointer for this row, call it row. And this is going to be our activations unembedding out plus input size minus 1, because we want the last row, times the vocab, which is the size per row. So then if the S element of this row is greater than max V, we set max index to S, and also the max V to the new maximum value. Okay, let's just print the index for now. Max index. And the index is 385. If I remember correctly, it might have been a different index in Python. Let's try this. So I want to print the token index. 385. All right. Same index. That looks very good. We are almost done with our implementation of the forward pass. The very last thing that we need to do, let's comment this out for now, right? Is to decode that index into the correct string. So all that should be is we want the offset into our, actually, I think we don't even need that. Let's just print a string with a certain size. And that size is going to be, what do we call it? Decoder tokens at our max index token ID. Get the offset, or rather get the size. And then do a decoder raw plus the offset of this token. Us, okay, that is looking pretty good. And let's try to print the entire, all of the tokens before. So just a simple for loop again. I equals 0, I is smaller than input size, I plus plus. And in here, I just want to print the correct token, which is going to be input at index I. This token here and here. No new line, except maybe at the very end. So we have a new line for our token. Okay. And I think this looks very good. This is basically the same result that we got in Python. So we have this as our input text. And from these tokens, we can derive that the next item in our sequence should be the token string us. And we get Carius as the final predicted name, which is exactly what we get in the input dataset. That's awesome. We have, I think, basically completed our first major goal of our model implementation in C, which is that we've fully recreated what we did in Python from beginning to end, where we take our input values, do the embedding with our token embedding matrix and the position embedding matrix. We have 12 layers of one attention block with layer norm and all the attention computations, and an MLP block with layer norm. These two have residual connections as well, which we implemented. We feed the output from one layer to the next layer. We have one final layer normalization and then a unembedding transform. We have implemented all of that. We have verified along the way that the results we get in our C implementation are the same that we get in Python. And with all of that, we are now able to predict the next element in the sequence. So I'm very happy with that. And I think the next step is now to do the backward pass. So let's do this. Okay, so for the backward pass, I think I want to have a look at our Python implementation again first. And let's explore how we do the backward pass in Python. It's actually very simple. All you have to do is call loss.backward. This works for any tensor, where PyTorch actually has a capability to trace back all the calculations that resulted in your final tensor. And it can use this graph of computations to take some output loss and trace it back throughout all of the computations that led to this loss. And what this allows us to do is to then go to each of our matrices and just do unembedding out dot grad. Let's just test it like this. And to get the final gradient of that matrix just like this. We didn't actually do it because we have a exit call right here. Let's comment out all of this and this as well and this as well. And we see that we get an error right now. And the error is that our tensor doesn't have, or multiple of our tensors don't have require grad set to true. This is relatively easy to solve. We just go back to our for loop up here and we do params. And for each of our parameters, we call, retain grad. That's the name of the function. And we now get an error that we can't do retain grad on a tensor that doesn't have requires grad set to true. And requires grad is just another parameter of the initializer. So we do requires grad equals true. And now we actually have another problem. So our backward call itself is now successful, but we can't access the grad member of our unembedding out tensor. And the reason for that is we did call retain grad on all of our parameters, but we didn't call it on our unembedding out matrix. So let's do that as well. Unembedding out dot retain grad. And now we're able to access its gradient. And what this allows us to do is to do basically the same thing that we did for the forward pass, where after each computation, we can check if the results that we get in our C code are the same results that we get in Python. So this makes our job a lot easier. And I think with this, we can get started with our implementation. So the first element in this chain of backward computations is the cross entropy loss, which we haven't actually calculated yet in our C code. So let's do that first. Let's go to our C code and let's maybe comment out all of this first, because this is only needed for inference, and all of this as well. And let's calculate the cross entropy loss. So if you go back to the iPad, the cross entropy loss, as we've written down yesterday, is calculated by taking the sum of the true probability for one class, for one element in our output vector per input sequence element, multiplied by our prediction for this probability, or the logarithm of that. Now, in our case, only one token is the actual true next token. So our y vector, like the true y vector, is a one-hot vector where all the elements are zero except for one, which is the index of the correct next token. So the sum reduces to just minus log of our prediction for the true token. Now, the value that we have currently in unembedding out aren't probabilities. They're just the result of taking our token encoding matrix and using that as a transform matrix for our uh, input vectors. So our first step is to calculate the elements, the probability of those elements. And we do that by just doing a softmax calculation per row of our output vector, output matrix. So right now, unembedding out is a matrix with input many rows and vocab many columns. And let's just create a second of those. And this is going to be our probabilities. And those are going to have the same dimensions. And let's calculate the softmax. So again, we will just have a for loop through all of our input elements. So input size. And let's create a pointer to the input values, which are going to be float pointer to activations, unembedding out, plus I times the vocab, the size of each row. And the first step in calculating the softmax is to find the maximum value. This is the story from yesterday where we want improved numerical stability. So we first subtract the maximum value of each row from each element. So we have a value called softmax max, initialized to minus infinity. And now we just loop through all of our input values. Actually, let's make this a const pointer, in plus the vocab. That's the end of one row. And we increment our input pointer. And we test if in is bigger than softmax max. And if that's the case, we set softmax max to this value. And that's it. Now we need to do another iteration where we calculate the exponent of the input value minus the max, and we build up a sum of those values. So we have another value called softmax sum, initialized to 0. And we just create another for loop where we calculate the value e to the power of our input value minus the softmax maximum value. And we want to save this into our output array so we don't have to calculate it again. All right, softmax out. So let's create a pointer to our output values. And this is just a float pointer to activations p out plus I times d vocab to find the correct row. And we can just do out equals e. And we also have to add e to our softmax sum. Okay, so the last step to calculate the softmax is to now loop through all of these values again. And now we actually need a out end pointer as well. So another for loop through all the output values. And we just do out times equals the reciprocal softmax sum. So 1 divided by the softmax sum, just so we don't have to do the division in each loop iteration. Okay, and just like that, we've calculated the softmax. So now if we go back to our equation, all we need to do to calculate the final loss value is to take the probability for the true token and calculate minus the log of that value. So let's iterate through our outputs again up to input size. And now we need the index of the correct next token. So if we go back up here, we have created an input pointer, which starts from the very first token in the text. And we'll just create a second pointer. We call it expected, which is just the respective next token in the sequence. So just the pointer offset by 1. For this token, which is expected at index I. And let's create a accumulator variable for the loss. And the loss is now just, let's call this CE, which is minus log of our activations. Oops, probability out row I and token index token. So this is the probability for the true next token in the sequence. And we just add that to our accumulator. And since we want the average loss across our input sequence, we now just need to calculate loss divided by the input size. And the value that we expect for our loss is around 4.13, if I remember correctly. Let's check this in a second. Let's first print our value. And we seem to be getting nan for this. Okay, I think I found one issue, which is that we never increment our out pointer. And we also need to reset this, out reset, for the next for loop. So out equals out reset. And let's try this. And we still seem to be getting none. And we actually need to reset our in value here as well. Out reset. Okay, we actually didn't declare in reset. This is just equal to in. Okay, and now we seem to be getting the same value, if I remember correctly, that we got in Python. So let's just print the loss again, 4.133, and that's the same value we got in C. So now our loss calculation is the same, and we can start calculating the gradient for the backward pass through this loss computation. Let's write down our equation for the cross entropy loss again, where we had the cross entropy loss of some value x, rather of the uh, one row of our output matrix, is minus log of our prediction for the true token. So I'm just going to call this yi hat. And yi hat was the result of a softmax computation. So let's go ahead and write that one out as well. So we have log of, since we saw yesterday that the calculation for the softmax is exactly the same, regardless if we have e to the power of x minus max or just e to the power of x. Let's use the simpler one of those. Let's do e to the power of xi divided by the sum of all the e to the power of x's. And to have an easier job of finding the derivative of this function, let's try to simplify it a bit. And the first thing that we can do is to split up this logarithm of a division into one log minus another log. So this is a common logarithm rule, which is that uh, the log of a divided by b is the same as log of a minus log of b. Oops, log of b. So we can rewrite this equation as minus log of exi plus, because minus minus, the log of the sum of all the ex's And now we want to find the derivative of this function. Actually, we can simplify this a bit further because we have minus log of e to the power of xi. So the logarithm computation and the e to the power of cancel out. So we just have minus xi plus this logarithm. And now we can find the derivative of this. So let's just write this down as d divided by dx is equal to d divided by dx of minus xi plus d divided by dx of this logarithm. And now we can see that this derivative is going to be different depending on the I. So if our I is equal to the uh, index of the true next token, so if I is true next token, in that case, the derivative is going to be -1. And if I is false, so if we are not on the correct token, in that case, xi is just a constant value, and the derivative of a constant is just 0. It's equal to 0. Okay, and now let's try to find the derivative for this part of the sum. And for that, we're just going to use the chain rule. So chain rule, which says that we should use the derivative of the outer function, so log of x in this case, and the derivative of log of x is just 1 divided by x. So in our case, that's 1 divided by the sum of all the exj's times the derivative of the inner function, which is the sum of all the e to the power of xj's. And let's actually make this a bit clearer by saying that the derivative is for the respective xi right here. And we do the same thing here, because that tells us how we are going to do, how we're going to find this derivative right here. So let's make this a bit clearer by writing the sum out. So we have e to the power of x0 plus e to the power of x1 plus e to the power of x2, just as an example. And let's say we want to find the derivative of this function with respect to x0. Well, in that case, all of these other e to the power of are going to be constant values. So the derivative of those values is going to be 0. So we only need the derivative of e to the power of x0. And e to the power of x, the uh, derivative of that is just e to the power of x. So that means that our derivative of the final sum is just going to be xi. Sorry, e to the power of xi, the only one that remains. And the same would be true for derivative with respect to x1. We would just get this one. Same for x2. So let's cut this. Our final derivative is this times e xi. That's the only one that remains from the sum. And now we can see that this result, let's actually make this a bit clearer, is just our softmax again. Okay, so if we write down the complete derivative of our cross entropy loss and softmax combination, it's just dx of minus log yi hat is for the true case, so for the actual correct token, uh, it's xi, or let's write this in the correct order. It's minus 1 plus xi, which we can just rewrite as xi minus 1. Actually, let's, since, no, I don't know. This should be yi hat. This is the result after the softmax computation. So the value that we take the logarithm of. It's not the input to our softmax, which is xi. This is important. So this is correct. If true, and if it's like if we are not looking at the correct token, so if it's the wrong token, it is going to be 0 plus yi. So just yi hat. So the derivative of this function is actually very simple. And just to make this a bit clearer, let's actually call this CE of x. So the final derivative of our cross entropy of the soft-maxed value, the combination of those. Actually, let's make this even more clear. Let's do soft max of x. Okay. The derivative of this combination of softmax and the cross entropy loss is going to be the result of the softmax minus 1 if so the probability for the true label minus 1 if it's true, and the probability if it's false. So This is a surprisingly simple implementation of the gradient for this combination, which should be very simple to implement in C. So let's do that. And I think the first thing that I want to do is to create a separate struct that is going to contain our gradients and another one for the activations during the backward pass. So one struct, gradients, and another struct for the activations for the backward pass. And let's maybe leave this empty for now, the gradient struct. And our activations back is going to contain uh, let's do this the following way. So activations back, the out array of an embedding is going to be the gradient at the output of this unembedding transform. Because what we've done is we've we are going to implement the backward pass through this P calculation and actually also the loss calculation. So the operation right before that is the unembedding transform. So whatever we get as the gradient with respect to the input of this operation is going to be the gradient with respect to the output of the previous operation. Okay, so it's going to be unembedding out. And let's allocate memory for our two structs. So we have a size t for the gradients, which is just going to be a struct gradients. And we do the same for the activations back. And let's create those two pointers as well. So we have struct gradients with the gradients offset. And here we have the activations back offset and struct activations back. All right. And let's implement the backward pass through softmax and loss. Let's maybe, I think we can just keep the loss calculation and just still print that. And let's create another for loop. Now, if we think about what we're doing here, um, most of the time, we're just going to copy the input of our backwards operation to the output. So, and like for one element in each input row, we're going to subtract one from this one element. So I think kind of the easiest way to do this is to just do a mem copy into activations back, unembedding out from activations e out. And this is going to be input size times devocap times size of float. And then in our for loop, all we have to do is to get the true token again and set activations back, and embedding out row I and element token, and just subtract 1 from that. And this should basically be it for our gradient calculation. So I would say let's try to print the result for this as well. Let's just copy this. We have activations back. Actually, unembedding out is correct. Input size times the vocab. Redefinition of parameters. I think I forgot to change the name after I copied. Yep, this should be gradients. Okay, we do seem to be getting a slightly different result for the sum of all the matrix values than we did in Python. So we get 0.008 in C and point a bunch of zeros and then 1.5 roughly in Python. But to be honest, I'm not too sure if this is really a problem because our embedding matrix is very, very large. We have uh, 64 times about 50,000 elements in our matrix, and it's quite possible that uh, the accuracy of Python sum or our sum is not perfect. Definitely isn't, but I'm not quite sure if this is actually the cause of this difference. But since we did check our activations p out matrix, let's just do this again. Um, let's check activations p out. Not sure if we checked this even. P out. This one is roughly 64. And actually, in Python, we don't have this matrix. Mm. So this is slightly difficult because we have an explicit softmax calculation in C, but we don't have the same thing in our Python code. Uh, so, and also the softmax sum should just be it should just be 64. That totally makes sense because each row sums up to 1. Uh, so I guess the fact that we get that value in C it's actually a good sign. And I think for now, I will not be too worried that our result is slightly different from the Python result. And we'll just continue with the backward pass and we'll compare the next result, which would be the uh, multiplication by the unembedding matrix. And let's see what the result for that one will be. So let's comment out this for now, because the calculation really is very simple. And we're just doing a mem copy from p out into an embedding out. And we do seem to be using the correct size for that. Let's maybe also check if we have the correct size of our struct. So we have activations back offset. Yep. And it does seem to be using the correct size here as well. So I think this should be fine, but again, let's just wait a bit and do the backward pass for the unembedding transform. Now, if we think again about our embedding or unembedding transform, what we did was just a simple like dot products of this vector times our input vector, resulting in one output vector. So you could just write this as a linear equation where you have e of x is uh, basically x1 times w1 plus b1 plus, let's maybe just put parentheses around that to make it a bit clearer, plus x2 times your weight plus b2. Okay, so this is uh, one column in this matrix and one row in this matrix, except again, in our code, we have it transposed. So both of these are rows in our code. So actually, we don't even have a bias. So this is just this. So calculating the gradient for that is going to be pretty simple. Um, we're first going to calculate the gradient with respect to the input, so with respect to x. And if you want the gradient with respect to x1, x2 and w2 would just be constants, so they would just fall away. And all you would get is that d loss with respect to dx1 is just the loss with respect to the output of this. uh, like this, multiplied by the derivative of that function with respect to x1. And that is pretty simple. It's just w1, because x1 derivative is just 1, and the other ones are just constants. And the same is true for the loss with respect to w1. Again, just the result of dl dfx times x1, because w1 derivative is just 1, and the other ones are just constant values. So this is basically it. This should be pretty simple to implement in C as well. So let's try to do that. And we have roughly the same loop that we did for the forward pass, where we loop through all of our rows. So we have uh, our input values, because we do need, uh, maybe it's actually a bit easier if we just calculate the derivative with respect to the input values first, and then with respect to the weights. So in that calculation, we don't need the input values, but we do need the weights. And we need our gradient with respect to the output of the unembedding transform. So that's just activations back, unembedding out. Now we don't calculate a dot product. We just, actually, we also need a pointer for the derivative of the loss with respect to our input. So dl din. And let's create that array as well. And this is just going to be struct lnf. So the input of our unembedding transform was the result of the final layer normalization. So in the backward pass, this is going to be the output that we're calculating the gradient for. This is the model. Okay, and let's use that value here. Activations back, lnf out plus I times the model. And let's maybe delete this. And let's think about what we have to do. So going back to this matrix, we keep one, it's actually dl d out, because it is the gradient. We fix one of those values. We go through all of our weights, and we calculate this input gradient. So since we have to like constantly add to this value, like one output value times the entire vector is going to be our gradient with respect to the input, then plus the next scalar value times one vector of our weight matrix is going to be another vector added to the previous one. So we need dl, din, end. Each row is the model long. And we need to reset this value after each row in the model matrix. Sorry, in the weight matrix. So this is just dl din. Okay. And now we need to add to dl din. But one thing that we should not forget is that uh, this matrix doesn't start out at 0. So we actually have to do a memset of activations back, lnf out, set it to 0, and it should be the entire matrix. Okay. And now we can add to those values. So we have dl/dn plus equals our current scalar dl/dout times our weight. Again, just translating this. And now, as we said, we fix one scalar, but we iterate through the entire input column, a dl, the input column, and the entire weight row. So we have to increment dl, din, and we have to increment our weight pointer. And if dl, din is equal to dl, din end, we reset this value. And we have to check if our weight pointer is equal to weight end. And in that case, we break from the loop. And here we also need to increment our out pointer, or actually the dl, dout. Okay, let's try to uh, go through this again. So weight end is going to be vocab times model. That should be correct. Yeah. Animating out is vocab long. Okay, lnf out. That should be correct as well. And we go through the entire weight matrix. Okay, let's try to print the output this. So we have activations back lnf.out. And the size of this, now it's a smaller matrix. So we have input size times the model. And let's see what we get. This should be a semicolon. Okay, we get minus 2.58. Again, this is a pretty small value, but let's see what we get in Python. Now that I'm thinking about it, maybe this isn't even the correct thing to do. Um, Let me just make sure. So if I print this, I get 1.477. What if I do unembedding in is equal to this? I don't think that this should matter. Let's try it anyway. Let's retain the grad on that. And we do actually get a slightly different result. So that's actually kind of interesting. Let's keep this and let's do the same thing for the input of cross entropy. So CE in is going to be unembedding out. And let's try to get the gradient of that. So CE in. Okay, no, this is, yeah, we get the same value exactly. So we don't need to do this. Okay, so let's retain the grad of LNF out in grad and print the sum of that. Minus 0.04, what we get in Python. Sorry, in C. Okay, so I just got something to drink, and I think I actually know what the issue that we're having is caused by. So if we look back at our loss, we divide it by our input size. So we get the average loss across the entire sequence. But we don't do this normalization for our backwards pass. So if we just print the value again that we are getting for the gradient of the output of layer normalization, it's minus 2.58. And the value that we're getting in Python is minus 0.04. So if we just calculate 2.58 divided by our input size 64, we do actually get the value that we're getting in Python. So the only thing that we need to do is to have another for loop here that simply uh, iterates through all the values again using the LDN reset, then it's equal to end DLDN plus plus. And for each of these values, we want to divide it by our input size. Maybe let's create a separate variable for that, float our input size, just one divided by the input size. Okay. And multiply by that right here. And let's print the value again. And now we actually get roughly the same value that we're getting in Python. So what this shows us is that the thing that we were worried about before, where we got a slightly different value for this output, was probably also caused by the same issue. We didn't divide by the input size. And if we do that, we just get like we get the correct value of our layer normalization gradient. So if we look at our diagram, we are now at the output of the layer normalization. So right here. And since that one is correct, we actually do know that all the previous values in the chain need to be correct as well. So we can be sure that our unembedding out gradient was actually correct. So Yeah, I think this is pretty good. Now, all we need to do is to calculate the gradient of, um, yeah, right now we just have the gradient with respect to the input of our unembedding transform, but we also need the gradient with respect to the weight that we use for unembedding the tokens. So let's create another pointer for that. And also, I think I want this one to be a const. These values don't change. Oh no, these one do change. Yeah, this one doesn't change. And we have DLD weight. And let's actually create a member in our gradient struct for this. So gradients struct, and I'm going to call this unembedding. Actually, yeah, I think I want to keep the same naming that we have for our parameters, where our unembedding matrix, which we also use for embedding, is called WTE. Okay. And we have a vector weight, which is the gradient of that matrix. And the dimensions of this matrix are again 50,000, so d vocab by d model. Okay, let's use that one here. So gradients, WTE weight. Okay. And if we look back at our equations, this, the loss with respect to the weights is calculated by multiplying our output gradient by the input value. So in addition to DL, DN, we also need our in pointer back. But this time it's actually going to be, actually, no, this can be const. Okay, so we have DL, the weight, plus equals. And I think we need to zero these values as well. So I think I'm just going to zero out the entire uh, activations back and gradients struct instead of doing individual mem sets. So right here, we can just do mem set memset activations back to 0. And this should be struct size of struct activations back. Yep. And we do the same for our gradients struct. Now we don't need this. So now we can just do a plus equals without being worried of reading uninitialized memory. And again, our weight is just DL, D out times the input. And now, in addition to incrementing DL in, we also increment in, and we increment DL, the weight. Out should be fine. Let's maybe move this to the top because they are inputs. Input weight out. And just like we've done for our DL in, we need to multiply our our weight gradient by the reciprocal of the input size. And we can try to print this as well, except we're going to have one issue, which is that we won't be able to check this against our Python implementation. Because in Python, we use, or actually in C and in Python, we use the same matrix for embedding and unembedding. So we have two gradients that are being summed up. One gradient comes from the unembedding step, and the other gradient comes from the embedding step at the very beginning of the model. So if we print the gradient of the matrix weight, we actually get this combined gradient and not uh, the gradient after the unembedding step. So we'll have to wait to see if this gradient is correct until we have completed the entire model. But I think that should be fine because the most important thing was that the gradient that flows through the model from the end to the beginning, that one is correct. And we did check that with this calculation right here of the total element sum of the uh, layer normalization output gradient. And actually, let's just run and print that one as well, or again. And now we seem to be getting a different result. Yeah, I think I know why it happens. We placed the mem sets at the wrong location. So they should be up here because we wrote to activations back already here and then we set it back to 0. So let's run again. Okay, and again we get roughly minus 0.0404, same value as in Python. And I think with that done, we can now go to the next layer, which is the final layer normalization. And I think it's a good idea to first do the derivation of this backward pass for layer normalization in writing, just do it by hand, and then implement it in C. All right, so let's first write down the equation for layer norm again, which is yi is equal to xi hat, let's call it that for now, times the weight plus a bias. And again, layer norm is a per row operation where each row is going to use the same weights and the same biases. And xi is being calculated by doing xi hat is being calculated by doing xi minus the mean of that row divided by the standard deviation. So let's also write down the equations for the mean and the standard deviation. So the mean was just the sum of all the x's divided by the number of elements in our array. Let's just move this here. And our standard deviation is the sum of all the xj's minus the mean across the vector squared divided by h as well. And let's maybe move all of these here. Okay. And let's start calculating the gradient. So the two easier ones are the gradient with respect to the weight and the bias. So let's start with those. So we have the loss with respect to the bi. That's going to be the loss with respect to the output of our function, so the yi, multiplied by the gradient of that function with respect to bi. And that is relatively simple because xi hat times wi is just a constant in that equation. So the result is just of the result of this part of the function is just 1 because the derivative of bi is 1. So we just copy over this part times 1. And that's the first gradient. Then let's do our gradient with respect to wi. And again, this is our loss with respect to yi times the yi divided by the wi. And that is just bi is the constant factor, so that falls away. The derivative of wi is 1, so we just take the xi hat. Okay, so that's our gradient with respect to wi. And the last one we want is the gradient with respect to our input values. And that is actually going to be a bit more difficult. So we're actually going to split it into multiple parts. And the first part is going to be the gradient with respect to xi hat. And then we can look further from that point. So we have our gradient with respect to xi hat, which should be dl with respect to yi again, times the gradient of yi with respect to xi hat. So that's very similar to the previous ones. It's just yi times, in this case, bi again, constant factor, xi turns into 1. So we're left with wi. And now we can calculate the gradient of the loss with respect to xi. And let's start doing that. dl with respect to dxi. And let's use our gradient with respect to xi hat as part of that calculation. So we do the loss with respect to xi hat. This is all just applying the chain rule times xi hat with respect to dxi. But we aren't really done yet because, yes, xi is part of the calculation to get xi hat. So this right here. But xi hat is also influenced, or rather, our xi also influences all the other elements of the vector through the mean and the standard deviation. And we need to take those into account as well. So in addition to these parts of the loss that we have right now, we also need to add the gradients of the loss with respect to xi hat times the gradient of xi hat with respect to, let's start with the mean, and then the influence of our respective xi on the mean. So this gradient. So let's think for a second about what we're calculating here. Basically, this part of the gradient describes how much does a change in xi influence the mean, and then how much does a change in the mean influence xy hat, and then how much does a change in xy hat influence the loss. So this is one more part of our loss calculation. But actually, this still isn't quite complete because, yes, we have our influence of our xi that we're looking at right now to the mean, but the same mean appears in the calculations for all the layer norm elements. So our entire uh, row that we are calculating the layer norm across uses the same mean. So if we change our value xi, that actually influences all the other layer norm values. So it isn't enough to account for the loss with respect to xi hat. We also need to account for the influence that the mean has on the loss of all the other x's. So we don't just have xi, we have a sum. Actually, let's just write this down. This is going to be a sum across j. of all the gradients where the mean has an influence on. Okay, so our xi influences the mean, and that mean influences all the elements across the entire vector that we process with layer norm. And actually, let's fix our indices. So this should be xj. Okay, and with this, we've now accounted for the influence of xi on the mean. And let's try to do the same for the standard deviation. Okay, so again, we have a loss with respect to dxi hat times dxi hat with respect to the standard deviation times the standard deviation with respect to dxi. But here we have the exact same story again, where our xi influences the standard deviation, and that same standard deviation is used across the entire vector that we process with layer norm. So changing our xi changes all of the layer norm results. And we need to account for that correctly. Okay, so again, we have a sum of all the values, change our index, okay, and now we've accounted correctly for the influence of xi on the standard deviation. But actually, there's one more part missing, where part of the standard deviation calculation is the mean. So we also need to calculate the influence of xi on the mean, which influences the standard deviation, which influences our xi hat. Okay, so let's do that as well. So we have dl that influences our, yeah, actually, let's just, let's use xi first with respect to our standard deviation. The standard deviation is influenced by the mean, and then the mean is influenced by our xi. Okay, but now we need to do exactly the same thing that we did before, where changing our standard deviation through the mean changes the entire vector. So we have a sum again. And the only elements that are part of that sum are these two. Okay, so let's copy this. Close the parens. Okay, and now we have accounted for all of the gradients that influence the loss from xi. So next up, let's calculate the individual gradients here. So let's start with this one. So just going to put this here. dxi hat with respect to dxi is, if we look at this equation, um, the basically we could decompose this division into xi divided by the standard deviation minus the mean divided by the standard deviation. And that would be a constant factor that falls off during the derivative. So all that remains is the derivative of xi divided by the standard deviation. And that's just 1 divided by the standard deviation. Let's maybe even color code this as well. So let's just make this green. Just so we know where we are. And let's do maybe this one next. So the derivative of xi hat with respect to the mean. And this is going to be very similar, but now xi divided by the standard deviation falls off during the derivative. So all that remains is -1 divided by the standard deviation. Okay. Let's also color code this. And let's do our final derivative for xi hat, which is the xi hat with respect to the standard deviation. And to do that, I think it will be a bit simpler to write our original equation a bit differently. So we have xi hat is equal to xi minus the mean times the variance to the power of -1/2. Because power of 1/2 is the square root, and since we're dividing by it, it's the power of -1/2. And now finding the derivative is pretty simple. It's just -1/2 times xi minus the mean times our standard deviation to the power of -3/2. And let's color code this as well. And now we have I think two more remaining, which are this one. So the derivative of the mean with respect to xi, and then the derivative of the standard deviation to xi. And then we actually have one final one, which is the derivative of the standard deviation with respect to the mean. Let's maybe color code this, and this should be green. Yep, I think that should be correct. All right, let's start with the mean. So we have the derivative of the mean with respect to xi. And what is that? So if we look at our mean calculation, it's really x0 plus x1 plus x2, and all the other x's that aren't xi just fall away. So the derivative of this sum is just going to be 1. And that is just going to be multiplied by 1 divided by h. So 1 divided by h times 1 is just, let's remove this. This is just 1 divided by h. Okay. And again, we color code that. And let's maybe put it up here. And let's try to do the same thing for the standard deviation. So the derivative of that with respect to xi. And now it's a bit more complicated because our xi's are, we first subtract the mean, then square that before we create the sum. So let's actually try to rewrite that a bit first. This is going to be the sum of xj squared minus 2 xj times the mean plus the mean squared. Again, divided by h. And all the parts of the sum that don't involve xi fall away. So we really just have to find the derivative to this part. And that shouldn't be so hard. So we have 2 xi minus 2 times the mean. And the mean squared is just a constant factor. So we have just this. And we can just write this a bit simpler as 2 times xi minus the mean divided by h. Okay, so relatively simple as well. And let's color code this. Okay, and now the final one is the derivative of the standard deviation with respect to the mean. So the standard deviation with respect to the mean. And for this, we can just refer back to this equation. And maybe for now, let's just write this out as the sum, as a sum of, if we find the derivative of this with respect to the mean, which is going to be minus 2 xj plus 2 times the mean, again divided by h. And let's rewrite this a bit as the sum of, basically we can factor out -2 from this because we can write +2 times the mean as minus 2 times the mean, and then just factor it out of the sum. So we get -2h times the sum over xj minus the mean. And so we put parents around that. And this is our derivative for the standard deviation with respect to the mean. And let's finally color code that as well. Oh, sorry, this was blue. Okay, so now we have a bunch of partial derivatives, so a bunch of gradients, and we kind of need to put it all into one big equation and find out if we can kind of cancel out certain parts of the equation to be able to simplify it. Now, let's do this step by step. So we start with our, again, this is just this part here, the derivative of the loss with respect to xi hat times xi with respect to xi, so 1 divided by the square root of the standard deviation plus the sum of this gradient times xj hat with respect to the mean, so minus 1 divided by the standard deviation, times mean with respect to xi, so 1 divided by h. Okay, and now the next line. So the sum of this gradient again times x with respect to the standard deviation. So uh, this one right here. So -1/2. Actually, let's just copy that. Copy this right here. Okay. And the result of that multiplied by standard deviation with respect to xi, so this. Okay, and now the final line. Now, the final line is actually kind of interesting because we have this derivative of the standard deviation with respect to the mean. which is this equation right here. And in this case, it's really valuable to just think about what this is calculating. So the sum sums up the differences between our input values and the mean. But if we think about how the mean is calculated, we basically undo the mean calculation. So the sum of all the differences of the input values to the mean should be zero. That's the definition of the mean. So actually, it turns out that this part of the equation is zero basically by definition. The sum of all the deviations from the mean should be zero. And since we multiply this zero by a bunch of other gradients, this entire sum within our gradient just goes away. It's equal to zero. So all that we're left with are the three rows that we already wrote down. So let's try to simplify this. And the first thing that we can see is that we have a multiplication by minus 1/2. And we have a 2 here. So first, we'll erase the minus, which will turn this into minus. And then we can erase the 1/2 because we have a 2 here. And now we're left with this. Actually, we can kind of do a similar operation for this line above, where this is just going to turn into a minus, and this will go away. And now we can kind of start to see something interesting, which is we have a minus at our variance to the power of minus 3/2, and we can rewrite this bit. So this to the power of 3/2, minus 3/2. Because remember that a to the power of x times a to the power of y is equal to a to the power of x plus y. Okay. 2 to the power of 3 times 2 to the power of 2 is 8 times 4 is 32, which is 2 to the power of 5. Just as an example. So we can rewrite this as squared times to the power of minus 1/2 times, well, same thing again, this times this. And now we have our to the power of minus 1/2 again, which is just the reciprocal square root. So we can now combine this. So uh, one of these with one of these, which just turns into this. Okay, so we can basically rewrite this as, let's make a, uh, yeah, let's write it in a new line for now. So minus the sum of dl with respect to dxj hat times xj hat. So this divided by or multiplied by this turns into xj hat. By the way, this should be the j. Okay, times xj times 1 divided by our standard deviation. Again, this is just this. Close the parens. And combining this with this turns into xi hat. And then we're just left with 1 divided by h. Okay. So now we can make one last modification, which is that we can pull this factor out of the sum. So we have this. And we can do the same thing down here. Okay. And this is basically, actually, let's clean this up a bit. Let's remove all of this. Delete. And this is now our final equation for the loss or for the derivative of the loss with respect to xi. And I think with that, we have basically all the ingredients we need to implement this part in C. Okay, so let's start with the simplest ones, which are the bias and the weight. So right here, we'll just uh, create another for loop over all of our input elements up to input size. And let's create our pointers first. So for the bias, we need a pointer of the loss with respect to the output of the layer norm. And this is just going to be activations back lnf out. So yeah. And we will need a pointer to our loss with respect to the bias. So activations back. Actually, this is gradients. Gradients, and we need to create a member for our layer norm. So struct lnf. And this is just a bias vector that is d-model elements long. And the same dimension for the weight. So this is just gradients lnf bias. And let's create a vector for, or a pointer for the end, which is just dl, dout plus dmodel. And let's write a simple for loop that just iterates through all of the elements. DL, D out will be incremented and the bias as well. Oops. Okay, and let's just add to this bias simply the gradient of the loss with respect to the output of layer norm, DL, D out. And that should basically be it for the bias. And let's see if this is correct. So we just loop through our gradients, lnf bias, and create a sum. And we get roughly minus 0.04, which is very similar. Actually, it should be exactly the same as the last result that we got, because the operation that we've done really is we've taken our output matrix and summed up all the. Actually, let me. Doesn't actually matter which matrix. Let's take this one. For each input element, we've just summed up all the values across all of our elements in the sequence. This is all that we've done. So we do actually expect the final sum to be the same. Okay, and let's do our weight gradient as well. So dl d weight. And that one is going to be our output loss times the normalized input value. So we don't have this normalized input value calculated. So I think we could, of course, like do the entire calculation again, where we calculate the mean and we calculate the standard deviation and calculate the normalized values from those. But I think it would actually be better to save the standard deviation and the mean in our forward pass and then just reuse those, those values in the backward pass. Okay, so let's go to our activations struct and add two vectors for the mean, which is going to be sequence elements long, and another one for the reciprocal standard deviation. So we can reuse those values when we have our backwards pass. I'm just going to copy over these vectors to here and also to our final layer normalization. And now our ln function call is going to take two more pointers, which are the reciprocal standard deviation and the mean. And here in our ln function, we will just set ln mean at index I to our mean. And the same thing for the reciprocal standard deviation. So ln standard deviation at index I is going to be this value. It's also just it's the naming to make it the same. Okay, and now we should be able to use those values in the backward pass. So let's create a pointer to, or actually, let's just get the mean and the standard deviation. So mean is going to be activations lnf dot mean at index I. And the same for our reciprocal standard deviation. And now we can just use those values for our weight gradient. So we have dl d weight, which is going to be our output gradient times the normalized value. So we need to iterate through xi. Let's do const float in. And this is going to be the input to layer normalization. Let's just look that up. Okay, the input is rest2 out of the last layer. So just this. And we need to add our row offset. So I times d model. And we also need to increment our input value and increment our dld weight. Okay. So now we do dl d out times the value of our input minus the mean times the reciprocal standard deviation. And this should give us the dl d weight value. Okay, so let's try if this is actually correct. And let's just print the sum of our weight gradient. And we've actually forgotten one thing, which is we need to add to our ln calls our standard deviation and mean arrays. So let's go to the first layer normalization. And in addition to our output, we now have the standard deviation, activations h at layer index, which is ln1 dot this. And we do the same thing for our mean values. Okay, let's copy this to the next layer normalization. And let's do this for the final one as well. And let's put in ln underscore f. Okay. And let's see what we get now for our gradient. Okay, we seem to be getting about minus 0.537. And let's see what we get for this value in Python. So let's do um, Let's do this first. Actually, let's do the bias. Uh, yeah, let's do the weight first. I think that, yeah, this is the one that we have in C. And what is the weight gradient? And we have 5375. What do we have in C? 5371. That's, I think, close enough. Let's do the same thing for the bias printed here. Minus 0404. And I think we had tested that in C as well. And I think it was actually this value, but let's just check again. Yep, that looks good. Okay, so we now have implemented the first two parts of our layer normalization gradient. And now we have this part here left. So let's think for a second how we're going to implement this. We have our loss with respect to xi hat, which we should find up here as well. And this can be calculated without any cross-vector knowledge. And we also see that all of them have a multiplication by the standard deviation, or rather a division by that. I think we can factor that out. And we should just be able to write the sum as a sum of the loss with respect to the normalist over the xi hat minus this divided by h minus this whole thing divided by h, and then multiply the entire thing by the reciprocal standard deviation. So let's start with these two sums first. These are going to be sums across the entire vector. So I think we should just be able to reuse this. Okay, and let's calculate this loss first. This is just our loss with respect to the output times the weight. Let's call this dl d in norm. This is going to be dl d out times the weight. And let's actually add a pointer for the weight. So weight, and it's going to be a const pointer. And this is just parameters L and F weight. Okay, so multiply by that. And let's not forget to increment this value here. Okay. So we have our loss with respect to the normalized input value. And let's sum all of these values across the entire vector. So we have one sum for our mean part of the loss, so for this part. And then we have another sum for the standard deviation part of our loss. And this one just multiplies this one with the normalized input value. So they're very similar sums. Let's call one of these mean partial. That's going to be our first sum. Then we have our standard, or actually just standard deviation partial. Okay, so mean partial should be plus equals dl dn norm. So just this value. And standard deviation partial should be this value times our normalized input value. So this right here. So let's put this here and let's do in norm as its own value. Okay, let's use it here. And let's use it here. Okay, after the loop, we divide both of these by the size of our vector. So the model as a float. And same for standard deviation partial. And now we can use those to calculate the final loss. So let's have another for loop here. And this time we want a loss with respect to the input. And let's create an entry for that in our activations back struct. And this is going to be the output of the second residual connection of each, or in this case, of the last layer. So we have again 12 layers, and we have a residual connection in here. And the gradient with respect to the output is going to be the sequence times the model. And we're just going to write into this. So activations back H11 rest2 out plus I times the model. And we have to use our DL dout again. So we need to first reset it. So DL dout reset. Let's do this first. DL dout is equal to DL dout reset. And we're going to increment it. And I don't think we need anything else. Actually, we do need the input. Yeah, because we need to calculate the normalized value again. So we also need to reset in. Okay, let's do that. In is equal to in reset. And yeah, now we need to calculate our loss with respect to the normalized input again and our normalized input. So both of these have been calculated up here. And now we just do dl in equals. Actually, let's maybe not sum it up in there. Let's create a separate variable. So dl in, initialize it to 0. And we will add to that the loss with respect to our normalized input. So dl in norm. Then we subtract from that our mean sum. So mean partial. And we subtract from that our variance partial times our normalized input value. Times in norm. Okay. And finally, not here, here, we multiply all of that with the reciprocal standard deviation. So just like this. And then we can save that final value in we have a naming collision. Let's do this. Set that to the LDN. And we also need to increment this pointer, the LDN, plus plus. Okay, and I think that should basically be it. So let's calculate our sum again. We have gradients, actually we have activations back, H, last layer, rest2, out. And this has input size times dmodel values. And let's print this. And we get 0.00277. And let's try to do the same thing in Python. So what is a good way to do this? Let's do lnf in for now. And let's use that here. And let's retain the gradient for that. So lnf in retain grad. And let's print the value. Dot grad dot sum. And we seem to be getting a relatively different value. Okay, so I found one mistake, which is we've forgotten to increment our weight pointer. And let's try, we have DLD out, we have in and DLD in. Okay. Now we get a smaller value. Let's compare this. Okay, the value in Python still seems to be smaller than that. And we also forgot to reset our weight pointer. So let's actually factor out all of these resets. And the same thing for weight. So we have weight reset, which is just weight. Weight reset. And these should be all the ones that we are using. We're using DL out, we're using weight, we're using the input, which we reset, and mean and standard deviation. And this should be okay. So let's print. And we're getting a apparently very small value. So let's add a couple of uh, digits to our printed value. Okay, now let's count this. 1, 2, 3, 4, 5, 6, 7, 8. And in Python, yeah, we get pretty much the same value. All right, so I think with this, we have finished the backwards pass for layer normalization. And if we look back at the derivation for this, I think that this is actually the most difficult part of the implementation of our backwards pass. Attention might be kind of in the same ballpark, but this is definitely one of the more complicated parts. Okay, so now before we continue with the next part in our architecture, I actually want to factor out this for loop into its own function. So we have one function to call for the backwards pass of layer normalization. So let's just go to the top, and just like we have a struct ln, I now want to have a struct ln back. And it's going to have the input, weight, and bias, which I think we don't need everything in here, but let's just keep it for now. And let's add our DL, D out, then our DL, D weight, and the same for the bias. Actually, this should be DL, D in. And I have another input, which is constant pointer to the loss with respect to the output. And let's just create this function. So we have static void ln back. Yep, taking a pointer to the struct ln back. And we're just going to copy our for loop from here. Okay, let's go to the top again. And paste it here. And now we need to adjust our variable names for this new struct. So we have ln sample count. DL, D in is going to be ln DL, D in plus I times ln in count as the number of elements per row. And our input is going to be very similar. We just have ln in plus this. In reset stays, we're doing a very similar thing for DL, D out. DL, D out. And also for the bias. And for the weights. DL, D weight. We also have to adjust our mean and standard deviation. They're just going to be mean and ln standard deviation. This should stay roughly the same. This should be the same. Actually, the model has to be ln in count. This should be the same. Yeah, I think everything else should just stay the same. So let's try calling this function. Actually, let's have a look if uh, yep, let's open this file again. Main.c. Just have a look if we have some values that we don't need. We need in. Do we need the input? Yes, we do. Do we need the weights? Actually, I forgot to change this. This should be ln weight. Yep. So we do need the weight, but I don't think we need the bias. We do need this. I don't think we need the output. Yep. We don't. DLDN. Yep. Yeah. Okay. All the rest should stay the same. And let's try calling the function. Did I forget a curly brace? Yes. All right. ln back is going to take this struct. So just construct it here in place. And let's copy out all the struct members. Let's do this. Go to the end. This should be a equals and comma point. Okay. So our input is going to be activations, and it's going to be the result of the last embedding. Sorry, the last residual connection. So res2.out. Our weights are going to be parameters lnf.weight. The LD out is going to be um, this. Mhm. Standard deviation is activations lnf.this, and very similar for the mean. The LDN is going to be activations back for the last layer, res2 out. Yep. The weight is going to be gradients lnf.weight, and same for the bias. In count is going to be the model, and sample count is input size. Let's print the result. This should be a float pointer. Okay. These pointers should be const. Should be const. This should be const, and this. And same for this. Oh, actually, this should be an array member. Okay. And I think this is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is the result that we got earlier. And let's just double check that we still get the same weights and biases. So we do gradients, LNF, weight, and print that. And we get minus 0.53. Let's do the same in Python. Actually, did I print the weights? Yeah. Minus 5375. Same thing, I think. I can't remember. Yes, same thing. And we have our biases, which were 0.0404. Yep. And let's print them here. Yep, same thing. All right, awesome. So with that, we have finished the backwards pass through layer normalization. And our next step is going to be the backwards pass through, if we go back, through the C projection transform of our MLP block. Actually, it's going to be the residual connection. But if you think about what the residual connection does, is it adds two values together. So the gradient is really just equally distributed. So both inputs get the same gradient. And at the point where the two split off, we just add the two gradients back together. So at this point, we don't have to do anything for the residual, but we do have to do that after the next layer norm. So after layer norm 2. All right. So let's try to do the backwards pass for the fully connected layer. And this is going to be kind of similar, but not exactly the same as what we did for our embedding matrix. So again, let's go through our input row by row up to input size I++. And maybe let's go back to the iPad for just a second. So our fully connected layer backwards pass is going to look kind of similar to what we did in the unembedding transform backwards pass. But there's going to be one difference, which is that in the forwards pass of the fully connected layer, we didn't calculate a dot product of one input vector with one transform matrix vector, so these two, into one scalar. What we instead did was we have um, one vector of our matrix, but actually the other direction. So in this diagram, it would be a vertical vector times one element of our transformed matrix equals one vector in our output matrix. And then for each column in our transform matrix, we calculate the vector and add it to a final resulting value. So if you remember, we had this diagram right here to kind of explain that these are exactly the same calculations. So we take one value here, multiply it by this vector, get this output vector, and just add all of these vectors together. So to do the reverse operation, we just take our output vector, because remember, if you have a sum of elements, the gradient just gets pass backwards through each of the elements that you add together. So each of these individual vectors is going to get the same output gradient, and we multiply that gradient by our one input matrix scalar to get the gradient with respect to the weight matrix. And our bias fits in very naturally with this as well, because it's just another vector that we add. So instead of having these three vectors, we would have another vector here for the bias. So as I just mentioned, the gradient will just get copied over to all the elements of the sum. So the gradient with respect to the bias is just going to be the sum of our output gradient across all of our sequence elements. So let's just try to do that. Let's create a pointer for the weight gradient. And actually, I think we have to first create those members in the struct. So that's going to be a struct H. We have 12 layers. And we have a struct called MLP within that. Again, just the same structure that we had before. Yep. And this is going to have a matrix for the weights, which is going to be, just look at this. Weights is going to be 4 times the model rows. That's the output dimension. And the model columns. And we have our bias, which is actually this should be C prediction weight has oh yeah, I forgot that they are transposed. Yeah, totally makes sense. So we actually have C prediction weight is actually I forgot that we need to have another struct in here called C projection. And this is going to have the members. Okay. And looking back, we have, yeah, it's same dimensions as our weight matrix. But we need to be aware that the matrix is transposed compared to a matrix that we would normally use for a transform. And here we have the model right here. Okay, so this is our gradients for this. And actually, let's just do the same thing for the result of the FC matrix, which has 4 times the model here and 4 times the model here. And let's do this for the result of Galileo as well. Actually, this is not a gradient. This should be an output. Yeah, let's create another struct in here. Struct MLP with I'm going to do this. I think I want to struct CFC and a struct Galileo. And we don't need one for C projection because the gradient is just copied from residual 2. And this is going to be D sequence times 4 times D model. Oops. And this is the same. Okay, so let's go back. So our weight gradient is gradients, the last layer, dot MLP dot C projection weight. And we do the same thing for the bias. Gradients. This is C projection bias. And now we need a pointer to our output gradient, which is a const pointer. We're not changing that. And this is just the pointer that we had as our input gradient for layer normalization. So the rest to output, dl d out. Okay. And let's just do the bias first. That one's a bit easier. So we iterate through our output gradients until we've reached the end of one row. Actually, this should be plus I times the model. Yep, but not here. This is just DLD out plus D model as our end of the row. And since we're going to, we take each, well, column in our drawing, but row vector in our matrix, and we read it repeatedly. And we add the entire vector to our bias gradient. So we need a reset value. Um, let's maybe do actually, we don't need to even iterate this. Yeah, I think we just need the end of this, and we need to check if dl out is equal to dl out end, and otherwise just increment these two values. Actually, I guess we do need a reset value for this later, because after this iteration, we need to reset it. Okay, increment these two, and we just add our output gradient to the bias. Okay. And I think this should basically be it for the bias. And let's check if this is correct. Let's use output dimension is the model. So radiance age 11 MLP bias. And let's get the sum. DLD out is declared here. Oh, yeah. Yep. DLD, yeah. Just this typo. Okay, we have again our very small value, which does make sense because we just sum up all of the columns in our drawing, but rows in our actual matrix. So we get a very similar value to what we got before for the layer normalization. And let's print this result as well with layer 11. Okay. And this is also a very small value. So I think this is probably correct. But I think let's maybe try this. Yeah, let's calculate the absolute value, which is not as small, and do the same thing here. Four eight seven nine. 4879 in Python as well. Awesome. So we've done the bias correctly. And now let's do the weight. For the weight, let's first reset our DLD out to DLD out reset. And then we're just going to do a while loop because this is going to be a bit more involved, the iteration of this. It's basically going to be very similar to our forward pass through a fully connected layer. And if we just remind ourselves what we discussed before, the gradient with respect to the weight is just going to be the output gradient times the input of this operation. So we need another pointer here. That's the input. This is just activations, H11, MLP, value out. Now we just need to select the correct row of this, and we need to be careful because this has 4 times d model elements per row. Okay. And uh, yeah, if we go back to the drawing, input is going to be a scalar value, and we multiply that scalar value by one entire row of our weight matrix. So we do dl, the weight, plus equals in times dl, d out, and dl, d out is going to be incremented at every step. And the same is true for dl, d weight. Okay. And our weight point is just gonna keep going throughout the entire weight matrix. But our out vector has to be reset. So uh, if DL out reaches DL out end, we have to reset it back to the beginning and increment our in pointer. And only after we've reached the end of our weight matrix, so DLD weight end, which is going to be input size times, no, the model. Let's just go back. Yeah, 4 times the model times the model. 4 times the model times the model. So if DLD weight is equal to DLD weight end, then we break out of the loop. Okay, and I think this should basically be it. So let's just check this. This should be good. This as well. Okay, let's try to run this and take the weight matrix, adjust the size. And we get 348. And 348 in Python as well. Awesome. So just like that, we have finished our backwards pass through a linear layer. And I think the last thing I want to do is to do the same thing that we did for our layer normalization, which is to just factor this for loop out into a separate function. So we just create another struct, call this fc back, and it is going to take the DL in gradient. Actually, I think we haven't done this yet. So yeah, actually let's do this before. Yep. So let's create a pointer to DL in. And this is activations back. H11. Value out. Mhm. And this is going to be relatively similar because we have our in value right here, this scalar value, and we just calculate a scalar gradient value. So we just have a running value here, dot, and this is going to be incremented by, let's think about this. The input is multiplied by the weight to produce the output. So the gradient of the input is just going to be weight times dl d out. So now we also need our weight matrix. And this is just parameters h11 mlp dot weight. And at this point, we need to set dl dn to our, or actually increment it by our dot product, reset the dot product back to 0, and then increment dl dn as well. Okay, and I think now we should be done with this as well. Let's print this value. And this is input size times 4 times bmodel. And this should be activations back, layer 11, MLP, value out. Yep. Okay, let's print. Okay, this is a very small value. So let's compare this with what we would get in Python. And I think, I'm actually not sure if this is possible. Let's maybe do if layer I is equal to 11. Let's do MLP the projection in is equal to, actually, uh, yeah, let's maybe just print the MLP value out. Not sure if this is being, I think we're losing the gradient information potentially. Or this might be the last value that was set to in the loop. Let's just try to print this. Value out dot grad sum. And we need to retain this gradient. Okay. And this is 58.97. Okay, I'm seeing one issue, which is we don't increment our weight pointer. Okay, we have weight times deal out. Okay, let's try now. 58.94. I think this is exactly the same that we got in Python. Yep. Awesome. So now we're actually done with the fully connected layer, including the input. And let's go back to factoring it out into its own function. Okay, DLDN, and also these two. And I think we also don't need the bias, but we do need the EL, the out pointer. And let's create the actual function, fc back, and it takes a constant pointer, fc, and we just copy, oops, this for loop. No, shit. Copy all of this into the function, and let's adjust the variable names. So input size is going to be sample count. Actually, might be good to uh, yeah, just leave this here for reference. Okay. And weight is going to be fc weight. The gradient of the weight is going to be fc dl d weight. Weight end is going to be the same. Bias is going to be fc dl d, oops, dl d bias. Output is going to be fc dl d out. Input is going to be fc in and fc dl dn. And I think this should have been it. Oh, the model needs to be uh, this is our in count, and the model is the out count. Same thing for this. This is fc out count, and here as well. And these two are going to be fc in count. Okay, I think this should be all of them. No, the model. Yep. I just want to make sure that there's no. Yeah, okay, this would have been a bit dangerous. We actually forgot a demodel constant. This is just ln, uh, oops, in count. Okay. No demodel in here. Yep, that looks good. And now let's call our newly created function. So fc back will take a pointer to our struct. And let's copy all the elements in here. Just like this. Let's do equals, comma, go back, make this a point, indent. Okay. And again, the input is going to be this. Weight is Uh, Parameters H11, MLP, C projection, weight. DLD out is this. Out is not going to be needed. So let's delete that from the struct. Yep. DL, DIN is going to be this. DL, DWeight, this. Bias. In count is going to be 4 times dmodel. Output is just dmodel. And sample count is going to be input size. And now hopefully we should get the same result that we got before. 58,944. 58,944. Okay. And hopefully the same for these bias and weight matrices as well. So let's take this. First, the bias for layer 11. 4879. Radians H11 MLP bias. Four eight seven nine. Yep. 4879. Awesome. And let's do the same thing for the weight. 348.7. 4 times the model. 348.2. 348.2. And this looks correct as well. Awesome. So we have also completed the backwards pass through the linear layer. So if we go back to our architecture diagram, we are now kind of in the middle of this MLP block. And the next step is going to be the backwards pass through the GalU activation function. And if we remember from earlier, the definition of GalU, so GalU of x, this is performed per scalar value of our input matrix. We have x times the CDF, the cumulative distribution function of the standard normal distribution up to our value x. And this CDF is the integral, so the area under the curve of our standard normal distribution function. And let's try to calculate the derivative for this function. So we have d with respect to dx of GalU. And for this, we're going to use the product rule. So d dx of of x times gx is equal to f derivative times g plus f times g derivative. So for our function, this should be d dx of x times the CDF plus x times the derivative of the CDF. And the first part is very easy because the derivative x with respect to x is just 1. So we just have CDF plus uh, the rest of this function. So oops, this part. So let's look at the derivative of our cumulative distribution function. And first of all, this is the definition of the normal distribution. And in our case, where we have the standard normal distribution, the mean is going to be 0, and the standard deviation is going to be 1. So in our case, this function reduces to 1 divided by the square root of 2 pi times e to the power of minus 1/2 times x squared. So let's just write this down. So we have 1 divided by 2 pi times e to the power of minus x squared divided by 2. And to get the CDF value, we actually need to calculate the integral of this function from minus infinity up to our value x. Which means we actually have to change our function variable. I'm going to call this t. bt. Yep. And we now need to calculate the derivative of this integral. And if our integral looks like this, it's just a continuous function, we can actually take a shortcut where the derivative of an integral is just the original function. So d dx of our CDF is just 1 divided by square root of 2 pi times e to the power of minus x squared divided by 2. And this is the derivative that we can use in our final equation. So I'm just going to replace this part with this. And this one reduces down to 1. So we can just leave our CDF. And let's just delete this. We don't need this anymore. And let's move this over. All right, so basically just like, actually, sorry, now you can see it again. So just like that, we found the derivative of Galileo. And the CDF, this is something that we calculate already as part of our original Galileo operation. And we could actually save this and then read it back. I think for now I'm just going to recalculate it in the backward pass. And we add to that our input value times all of this. And let's try to implement this in C. All right, for now I'm just going to do this in line right here. And I think we might actually be able to copy this over from here. So we take all of this. Our input value is now, actually we do need the input, but we don't need the output anymore. But we do need dl d out and dl d out end. So this is now going to be activations back, Galileo out. And we want to find dl d in. So this is going to be a pointer, activations back, again, our layer, MLP. Actually, do we not? Um, okay. Oh, I think my autocomplete is broken. This is going to be CFC out. And this should basically be all we need. And now let's do DL out until DL out end. We increment our input, we increment our DL D out, and we increment our input gradient. Okay, and now, according to our derivative, we calculate, or we take this result of the CDF and we add to that. So this is going to be the value with respect to the in, the CDF, plus our input times 1 divided by square root of 2 times pi, 2 times m pi, which we need to convert to a floating point value. And 1, 2, 3, 1, 2, 3, 4. I think we have one too many parentheses. Mm, yeah, I think this should be yeah, this should be it. And this should be a floating point value as well. 1 divided by 2 pi square root times e to the power of minus, let's do this as minus 1/2 times in times in. Okay, and that should be it. Now we have the derivative of the Galileo function with respect to the input. But to get the final input gradient, we now need to multiply this value by our output gradient. So dl d out times d Galileo d in. And that gives us the gradient of the loss with respect to the input of Galileo. And let's just make sure that we have incremented all the values, dl d out and dl d in. Yep. And we have input size times 4 times model. Okay, that seems to be correct. And now let's check if this actually gives us the correct value. So input size times 4 times d model. And this should be MLP CFC dot out. And we should use the activations back. All right. And it might actually be wise to do the same thing that we did for the forward pass, where we just defined a variable that we call layer I. And for now, it's just going to be 11, so the last layer. And then once we put this into a for loop, we can change this relatively easily. So we can change all of this to layer I. And we just leave this as is. And let's print this. And we get 14.58 roughly as our result. And let's try to do the same thing in Python. So we want the output of the gradient with respect to this input to our Galileo function. So we have to do retain grad on that. And then we just get the gradient. And I think, did I use the absolute value? Yeah, I did. All right, and let's print. 14.579. Awesome. That looks 579, 14.579. Yeah, that looks very, very similar. Awesome. So that was pretty easy. And the next step is going to be FC back for our CFC transform. So that's just going to be another call to FC back, where we use IP CFC. Actually, the input to this layer is actually res1 dot out. Yep. Actually, no, sorry. It's the second layer normalization. Because if we go back to our architecture diagram, the first thing before our MLP transforms is layer normalization. So we just use that as the input. Weight is going to be CFC dot weight. The output gradients are MLP dot Galileo dot out. So sorry, uh, MLP CFC out, the values we just calculated. The input is going to be the gradient with respect to the second layer normalization. So we have to create this. MLP, yep, and this is going to be a struct ln2. It's going to have weights and biases, just like this one. And in our activation spec, we also want this. So let's call this ln2. And it's also going to have input size times demodel elements. So now we can use that as our input gradient, ln2.out. The weight is going to be cfc.weight and cfc.bias. And the input count is going to be demodel and output count 4 times demodel. And I think this should be fine. MLPC. Yep, that looks okay. So now let's print, well, kind of everything. So let's start with uh, the input gradient. So activation spec, ln2.out, and we have input size times demodel values. And we get 54.635. And let's compare this with our Python implementation again. We do ln2out, retain grad, and print 54,638. 54,635. So very similar. I think this is correct. And let's do the same thing for the weights and biases. So weights is going to be demodel times 4 times demodel. If I remember correctly. Yep. All right. Let's print those gradients. H11 MLP CFC weight. Five to 3.4. Let's just put this into a comment and let's do this matrix gradient of layer 11. 5 to 3.45 in this case. Awesome. And same for the bias. And we get 3.66. And the bias should be 4 times demodel. And we get 3.66. Awesome. So this works as well. Okay, so I think we can go to the next layer normalization. This should be pretty simple as well. We just copy our LNF backwards call. And this one is going to have res1 out as its input at layer index. It's going to use parameters h layer I second layer normalization weight. DLD out is going to be this vector or this matrix right here. The standard deviation is going to be h layer I dot ln to this, and very similar for the mean. And the input gradient, yeah, this one is going to be res1 out at layer I, very similar to this. DLD weight, also going to be h layer I ln to weight and bias. Okay, and let's print the input result as well. So input size times d model ln to, oh, actually, okay, let's do weights first. Weights. And this one doesn't exist yet. Res1 out. So let's create it. Res1 out. But actually, this isn't correct. I'm just remembering because, as we said earlier, we actually need to combine the gradient of this layer normalization with the gradient that we had at this point. Basically, we need to do the backwards operation for our residual connection, where the gradient just splits up and both parts of the sum get the same gradient. We now need to add the gradients after this operation, the two back together. So I think the cleanest way to do this is to just have a second array in here, which would have the same size. And it will be the gradient with respect to the second input of this residual connection. So in two. And then we will sum these two together into res1 out. I think this is the way we should go. So in here, the input is still going to be res1 out. This is still correct. DL, D out is correct. Yeah, this and this as well. But this one needs to be different. This one now needs to be res2 dot in2. This is going to be the same, and this as well. Demodel weight. Did I actually do what I want to do? I think we didn't check this yet. Okay, so we have 5.919. And let's see what we get here. This is going to be layer 11 and the weight. And we get a very, very similar result, 5.93 versus 5.91. And let's do the same thing for the bias as well. And we get 11.73. Let's check the bias. 11.703 in this case. Yep, very similar. And now let's check the input gradient. So this one, and this one is input size times the model. Okay, and we get 1.944. Okay. And let's take I think actually this might not be exactly what we want because res1 out probably has both gradients. Yeah, I'm pretty sure about that. Let's do ln2 in is equal to this value. And let's use this one here. And now let's get the gradient of this one. Okay. And we get a slightly higher value. I'm not quite sure. I think it's very possible that the gradient that we are getting here is actually the sum already of the two gradients. So the sum of this gradient at this point, so at the output of our MLP block, and the sum of our input of the layer normalization. So I think the easiest way to see if this is the case is to just calculate that as well, because that's something we need to do anyway, and should be pretty easy. Then we can see if that's right. Actually, we can make a second guess by doing not this and taking it directly. And if we get 3.26 again, then we know that it is actually the combined gradient. Yeah, okay. So it very much seems like we have to do the residual connection first. So let's take the code that we had in the forward pass and execute it again in the backward pass. So this code just takes two inputs, which in our case are going to be activations back of res2 out and res2 into. And those two gradients are going to be combined into the output of the first residual connection, which, yep, okay, we did already create. The output size is input size times the model. So that looks good. And we sum those two values. Okay, and let's just read the output sum. Input size times the model. Yep. And this should be a 3.26 if I remember correctly. And we do actually get 3.26. Awesome. So think we've made really good progress so far. We have completed the first half of our layer, and the next step is going to be probably the most difficult, if not one of the more difficult parts, which is the backwards pass through the attention block. If we remember from yesterday, the last part of our attention calculation is the final projection. So we take our 768 dimensional vectors and we multiply them by a matrix that is 768 by 768 dimensions. And this gives us our final output values. Let's just look at that in code. Yes, that's this function right here. So we take in the resulting combined v values. So we have created this weighted sum of our z values, sorry, of our v vectors, resulting in the z matrix. And the way we've done this in code is by just kind of putting together these slices of the Z matrix. So we can see here that we kind of select one slice for our Z matrix and write into that. And we do a final transform of this Z matrix by our attention Z projection matrix, which is dmodel times dmodel. And the first operation we need to do is to reverse this. So we have a call to fc back. And its input is going to be attention dot z out. This is the matrix that we used right here as the input. And actually, we can just probably copy over a bunch of these values, or at least take them as a reference. Our weights, that's correct, are going to be these weights. dl d out is going to be this. So if we just look back at the diagram, we are at this point where we want the output with respect to the gradient with respect to the output of our first residual connection. So this one, our input activations, I think we need to create those first. So let's make a struct called, I think we call it attention. Yep. Let's actually just copy this and delete the ones we don't need. With attention, we have our, this one we actually don't need because it's going to be contained in the res1 struct. But this one we do need. This is the matrix that we are going to produce right now. We will need the result of softmax. Yep. And this is going to be the gradient with respect to the input of the softmax. And then this is going to be the final linear layer. Okay, so I think this should be fine. And our gradient struct will also have Actually, it's maybe just take the gradients right here, this, sorry, the parameters, and copy them here. So this matrix, C projection, has 768 by 768. So D model by D model. And the bias should just be a simple vector that's D model long. And the C attention matrix, if we remember, it converts our D model vectors into 3 times D model vectors. So it should be 3 times D model. So the weight matrix is going to be, I think, D model times 3 times D model times 3 times D model. And those are our gradients. And while we're at it, let's just do the first layer normalization as well. All right, let's continue here. So DLD in res1 was our output here, and DLD in should be attention Z out. Yeah. DLD weight should be attention C projection weight. Attention C projection bias for the bias. The in count is demodel and the out count is demodel as well. And we don't need this anymore. Yep. And let's check if the result of this is correct. So we want, let's do DL in first. So this matrix. And it should be input size times the model. Yeah, because our size just stays the same. And we have 10.856. Let's check if we get the same in Python. So we want uh, yeah. Wait, this is the input? Yes, yes, this should be fine. Retain the gradient and print it. And we get 10.857 in this case. That should be fine. All right, and now we get to the slightly more difficult part. So let's think about what we did. Let's maybe just make a new drawing for this. Okay, so our Z out matrix was 768 by 768. And actually, no, it was input times 768. And for each row, so for each element in our input sequence, we had a concatenation effectively of all the 12 weighted summed v values, v vectors. Okay. And we can basically just reverse the operation. And for each of these output vectors, kind of reconstruct how they were created. And each of these vectors was, so like this, the weighted sum of one row of our attention matrix, where these values were created by softmax, times the respective v vector, which was the result of the very first matrix multiplication with the d-model times 3 times d-model matrix, giving us our v vectors. So what we need to do is we need to kind of redistribute the loss to all of these v vectors weighted by the softmax results. Because basically this is very similar to a matrix times vector multiplication, where your input vector is, in this case, probabilities that sum up to 1. So like 0.1, 0.5, 0.05. And uh, multiplying the transform matrix row by row with each column of your input, so the probabilities, is going to give you the gradient with respect to, I was going to first give you the output, and to get the gradient, you just kind of measure how much contribution your respective transform matrix vectors had on the final result. Okay, so we've done a very similar thing for our linear layer, and we're just going to repeat this for this weighted sum. Again, just try to kind of reimagine this problem as having an input vector of probabilities that you transform by your v vector matrix. And if you just want like an intuitive sense, if you imagine that your v vector has been weighted by, let's say our v1 vector has been weighted by zero point 0.5, it contributed the most to the final loss. That's why we multiply the loss by the input, so by the 0.5, to get the output, or sorry, to get the v vector gradient. This is how much we need to change our v vector, because it was weighted by, in this case, 0.5. Right, so let's try to do this. So let's create a for loop that I think for the attention calculation we looped through the heads first and then through the cues. So I think we can just do the same thing again. Okay, this was only half of it. Anyway, das heißt hier head I up to 12, we have 12 heads, and increment this by 1. And now we increment our hue. Maybe it's a bit misleading to call this hue. Uh, let's just do the same thing we did before, where this is just called I, which is going to be the actually. Uh, yeah, let's call this I for now. And we're going up to input size. Okay, and let's start to create our pointers. So let's get the pointer to the output gradient first. So we do float pointer, and we're going to call this dl dout. And this is going to be inside of our Z matrix. And we're going to select the row by our input, so I times the model. And then we need to offset by our current at index. So plus at I times, I think we call it decay, which is the number of elements per head in this vector. Yeah. And how do we want to do this? I think the best way is to also loop through our attention matrix and take each scalar value from the attention matrix, which is our weight for the respective v value, and multiply it by the uh, v vector. And this is going to be our dl with respect to, let's call it dv. And this is going to be actually, this might be a bit more complicated because we like what exactly our dl dv is depends on. Okay, let's maybe write this out first. So we have another for loop that goes through the v's and initialize it to 0. It's going to count up until I, and actually including I. And we increment that. Okay, and now let's create the pointer to our v's, which is going to be activations back for our layer, tension, and here we need C attention out, because our v vectors are the result of transforming our input values to the attention block by the C attention matrix. We need to offset this by our VI index times 3 times d model, which is the number of elements per row. Yep. Offset this again by 2 times d model to get to the rightmost third, including our v vectors. And then offset that by our head index times decay. Okay. It looks complicated, but I think this is correct. With our C tension output gradient, let's just make sure that this has. Can we just go to that? Tension, C tension out. Yep. 3 times d model. We go to the respective row, offset this by 2 times d model, and offset it again by our head index. That should be good. We want a DLDV end, which is going to be this plus decay. It's just 64 elements. And we want our scalar value, which was the weight that we used to multiply our v vector. And we're going to call this factor for now. And our factor was going into our activations layer I, attention. It was the result of softmax. So S out for our head. So head I. The row is going to be I. This is our current V row. Again, remember we're just in our attention matrix. We're going through these elements one by one in one row, one query row at index VI. Yep, this is the factor of our respective VI. Okay, that should be it. And now we need to multiply our DLD out. And actually, since we loop over the same output vector multiple times, let's put this in here as well. And now let's have another for loop. This is going to be dl dv not equals to dl dv end. We increment our dl dv. We also increment our dld out. Okay, yeah. So this pointer is not influenced by our VI, which means we are always using the same output vector, and we're going to weigh this output vector gradient by the weight that we used during the forward pass to get the gradient with respect to the input of this weighting process. Okay, so this is just dl dv plus equals factor times dl dout. Okay, and I think this should be it. So we've now calculated the gradient with respect to our v vectors. But for now, we don't really have a way of checking if this is correct, but uh, that should be fine. So let's do the gradient with respect to the weights that we used next. So each v vector was weighted by a certain factor, and we now want to calculate the gradient with respect to that factor. And this is going to use kind of the same infrastructure that we built up here, where we have our output gradient and our inputs. Actually, we do need the inputs. So let's do const float v. Um, so this is almost the same as this, but we want activations of this layer. Yep. Offset by this row index plus 2 times the model plus our head index. Okay. And now we need to accumulate the derivative of this factor. So let's create a value called dot for now, which is kind of the dot product of the v vector and the output gradient initialized to 0. And let's do dot plus equals our current v, and this needs to be incremented as well, v times dl dout, but dereferenced, times dl dout. dl dout is being incremented here, v here. Okay. And after we've done this, we need to save this value into our softmax output gradient. So let's just do Let's copy this and use activations back. And I think we just called them the same. Yep. It's going to be plus equals dot. All right. I think this should be fine. Let's maybe have a look at our Python code. So I think I might have one idea how we could at least test if our v vectors are correct. Because right now we have only filled the v third of our C attention out gradient matrix, and the entire rest should be equal to 0. So if we calculate the sum over the entire matrix, we should just be getting the same as in Python if we just use the V matrix. So this should be attention dot C attention out, and let's print this value. Uh, and because, yeah, it should be a float pointer. All right. And we get 3.117. So let's get our V matrix and do retain grad on that and print the gradient of this. And we get 3.116. Awesome. Okay, so we know that we're not completely off, at least. Now let's continue with the backwards pass through softmax. So our softmax computation looks like this. We have softmax of an input value xi, and it's e to the power of xi divided by the sum of e to the power of exj. And we want to find the derivative of this function. And the first thing that we need to think about is that we kind of have a similar situation that we had with our layer max, where one xi, one input value, has influence on all of the output values because we create this sum. So what our gradient will look like, if we just write it down, is we have a dl with respect to dxi, and that's the loss with respect to the output of our softmax, which for now I'm just going to call yi. So dl with respect to yi times, again, just the chain rule, dy with respect to dxi. But since our one xi has influence on all of the output values, we actually need the sum over j of our loss with respect to dyj, and we also use j here. Okay, so this accounts for the fact that our one xi has influence on all the softmax results, and those softmax results have influence on the final loss. So now we can take, and by the way, this is what we just calculated. So we now have the loss with respect to the softmax output for each position. And we now want this gradient. So let's try to calculate that. And one thing we will see when we look at this function that we're trying to find the derivative of is that the gradient depends on whether the index of the element that we're trying to find the gradient for appears at the top of this division or not. So maybe I can write this as an example. Mm, yeah, okay. Let's call this dyk divided by dxi. So k is just iterating over all the possible output values that our xi has an influence on. And yk, let's just write this out in a bit more detail, is e to the power of x k, because the value that we're looking at is k, divided by the sum over j of all the possible, of all the input values. And this is now kind of where it makes a difference whether our k is equal to our I. Because if it is, then the derivative of this part in particular is going to be different. And let's write this out. Okay, so for the gradient, we're going to use the quotient rule, which says that if we have a derivative with respect to x of f of x divided by g of x, the result is going to be f derivative times g minus f times derivative of g divided by g squared. So let's try to follow this pattern for the derivative of this function right here. I'm just going to move this to the side. And let's first do the case where our k is actually equal to I. So this is dyk with respect to x k. So in this case, the derivative of exk is actually just going to stay as exk, because xk is the uh, variable that we're creating the derivative with respect to. So at the numerator, we have, maybe let's write this out fully first. So we have exk times g, which is this sum, minus f, so exk times the derivative of the sum, okay, divided by sum squared. And the derivative of our sum of all the e to the power of x, we've had this case before, is just going to be the 1 e to the power of x that we are creating the derivative for, so exk. All the other ones are just constants, so exk. And now we can factor out exk times the sum minus exk again divided by this sum here. And now we can observe something, which is that this and one of the two sums is just our softmax result. This is just this right here. So we have yk times, and then the remaining part is going to be uh, the sum minus exk divided by the sum. And we can pull this out into this minus this, and this is just equal to 1, and this is just our softmax again. So our final result is times 1 minus our softmax result again. And again, this was for k is equal to I. So let's do if k is not equal to I. Okay, and let's create this from scratch. So if k isn't equal to I, then the numerator of our softmax is just going to become 0. It's just a constant factor. So we have 0 times g, which is the sum, minus f, which is exi, times the derivative of the sum. Oh, sorry. That's actually not correct, because this is just our uh, unmodified f, which is exk, and the sum just reduces to exi, because all the other ones are constants. Okay, so now this part falls away. Now we can basically do the same thing that we did for the other one, where we have this part and then this part. So this is the softmax result for k. So yk, sorry, actually minus yk times yi. And these are our two results. So let's go through an example of this sum here, this one. Uh, yeah, let's do it down here. So copy that. And let's just do this for x0 for now. Okay, and let's put this to the side. So dl dy j becomes dl dy 0, dl dy 0. This is the one we calculated before. And we multiply that by what we just calculated. And in this case, for x0, I is equal to k. So we are creating the gradient with respect to x0. So we need to use this side here. So let's just insert our resulting gradient, which is just y0 times 1 minus y0. Okay, this is the first part of our sum. And for the second part, we have dl dy1 times. Now let's use this part because now I isn't equal to k. The gradient is towards x0, but we now have k equal to 1. So this is our value here. So again, k is equal to 1 now, and I is still 0. So this is now the second part of our sum. And for the entire rest of the vector, I won't be equal to k. So we'll just continue like this, y2 and y2. And let's try to simplify that. And the first thing I want to do is to get rid of this. So the way I want to do this is I want to take these two, multiply that by 1, minus these two multiplied by yo. Basically just multiplying all of this out. And let's write this down. So we have dl dy0 times y0 minus dl dy0 times y0 times y0. Okay, I mean, now we are looking at something that looks very similar to the rest of our sum. And we are actually able to reduce this just a bit further by slightly rewriting this part here to plus, and then we just multiply all of this by -1. So kind of like this. And now we go basically just one tiny step further where we move this sign, which is really just a multiplication by -1 here. And now we get exactly the same that we have in the rest of our sum. So let's do one final simplification of this. Let's do, and again, you can just imagine that all of this stays exactly the same. Okay. So we have this first part, dl dy0 times y0. This and this and all of the other values in our vector. So this is plus the sum of, let's call this j, dl dyj times minus yj times y0. And now we can basically just do one final simplification where we pull out our y0. Okay, so this and this, and multiply by dl dy0 plus, actually I should uh, make a bit clearer that all of this is inside the sum, but our first step was to move y0 out of the sum because it isn't uh, iterated on by the sum. So it looks like this. And now we have sum over j of dl to dyj times minus yj. Okay. And maybe let's do one final simplification where we just take this times minus 1 and move it out of the sum. Okay, and this is our final result for y0. And now we can just generalize this to not just y0, but all of the elements for a vector. So we have done this specifically for y0 here, but we could have just replaced 0 with uh, I in our case, and all of these equations would have still been true. This wasn't like a rigorous proof of everything, but I hope that this made it kind of more intuitive of why this works. So I guess we can just, yeah, let's just write the final version down. So we have dl with respect to dxi is equal to all of this. This is an I, this is I, and now we're done. So this is the final result of the gradient of the loss with respect to the input of our softmax calculation. Okay, let's do the C implementation for this gradient now. And I think the first thing we should do is to calculate this sum. So the sum is really just iterating over all of the elements in one row of our output attention matrix, both the gradient and the uh, original forward pass attention matrix, multiplying the two and yeah, just summing up all the values. So let's create a variable called maybe row sum. Actually, it's just called sum for now. And we need to iterate over all of the values in one row. And let's just create an iterator called Uh, let's just do K. Actually, no. Let's do J. This is fine. J up to, or maybe let's, um, yeah, let's actually just use our existing for loop for that. So let's move our sum up here. And in this last step, we're just going to do sum plus equals, and dot is our gradient. And we did plus equals here, but we this should actually be correct because plus equals is only if we had actually mm, no, yeah, this is fine. Um, because each element of our input sequence is in one row on its own, and we don't have multiple batches, so our gradient starts at 0 in this case. And we multiply dot, again, our loss with respect to the softmax output by the original softmax output. And this is just the factor that we used before. Okay, and this gives us a sum, this one. And now we do another for loop, size t j0, j up to and including I. Maybe let's just call this q because this was how these values were originally calculated. So we have to I up to I, and later we can rename I to ki. Actually, no, sorry, this is wrong. This is ki, and this I should be qi because we have one fixed q per row, and then we iterate through all the k's. So one query and multiple key values, and we increment ki. Okay. And let's write the result of that into attention, which is just another matrix that's sequence times sequence items in size. Okay. And select our element. At I is the index of the attention matrix. I is our query index, and ki should be the index within each row. This is our uh, this loss. So the loss with respect to the input of softmax, and this is going to be yi, which is this factor again. So factor times the gradient, which is this in parentheses. Actually, let's make a separate variable for that. So this is dl factor, just the gradient. So dl factor minus our sum. Okay. And I think with this, AI is the column index, and yeah, vi should actually be ki in this loop. Mhm. Factor and dld factor. All right. I think this should be fine. And we have now calculated these values. Sorry, uh, the gradient for these values here. And the remaining values are 0. Okay. So just like this, we now should have the gradient with respect to the input of our softmax operation. And just like before, this is going to be basically impossible to check because we can't easily get the values for one individual head in our Python code. So the next possible location to check if what we've done is correct is going to be comparing the entire C-attention matrix. So now the next step is to calculate the input of the gradient with respect to the inputs to this attention matrix. And if we remember from yesterday, the individual elements in this matrix were calculated by creating the dot product between one q vector and multiple k vectors and dividing that by the square root of dk. So all we need to do now is basically do the reverse operation. So this is again going to be a loop over all of the k's. So ki equals 0. Ki is up to I. And in this loop, we um, we now want to calculate the gradient with respect to the q and the k vectors. So first, let's create pointers for those. So dl dq. Let's just use this as a template. dl dq. And our q vectors are in the first third. Okay. 3 times. Yep. This should just be I. Yes, because that's our q index. And then we have our k's, which are in the second third. And we want to use ki as our index for those. Okay. And in addition to the gradients to Q and K, we also need Q and K themselves. So this is in our activations struct with the same indices. Let's put this here. And the same for K. So const activations. We choose our row with Ki, offset by dmodel. Okay. And this should be decay. Although I think we actually don't need both ends. We just need one end because the vectors are the same length. And let's get our dl d out. Which is this entry in our attention matrix. And I think that all we need to do now is to have another loop that goes until dl dq is equal to dl dq end. And we increment dl dq and dl dk. And to get the gradient with respect to q, all we need to do is take our output and multiply it by the original k value. So this is very similar to all the uh, matrix multiplication backward passes we have done so far. So dld out times the original k value times the reciprocal of the input size. Sorry, the reciprocal of dk, which I don't think we have. Dk. Let's just do the square root for now. Dk. Oh, actually, no. This is a constant. This is r square root k. Yep. And very similar for dl dk. dl out times q times this. Okay, and now also increment q and k. And I think that this should basically be all we need to do. Again, I'm not quite sure if what we've done so far is actually correct because we weren't able to check our results for a very long time. But if we've done everything correctly, we should now have the correct results in our see attention out matrix. So let's just print the sum. Okay, and we get 6.97. And let's see what we get in Python. So we want, uh, yeah, we want this matrix, retain the gradient, and then create the sum over all the values. 6.96, what do we have here? 6.97, holy shit, we actually did it. First try. Um, awesome. That was easier than expected. So this entire block is our attention gradient. Uh, we first calculated the gradient with respect to just thinking with respect to our v vectors. Yep, and with respect to our attention matrix after softmax, we um, I really can't believe that this just worked. uh, we rederived the derivative of softmax to get the gradient with respect to its input. And then from there, we calculated our Q and K vector gradients. And now we've really done the most difficult parts of this model. Um, actually, here. So we now have our Q, K, and V gradients. And now the very last thing that we need to do is to do the backwards pass through the uh, C attention matrix transform. And this is just another call to FC back, where our input is going to be layer normalization 1 out. The weight is going to be C attention weight. The LD out is what we've just calculated. So attention, C attention out. The LD in is going to be uh, LN1 out. Let's create this in a second. The weight gradient is going to be C attention weight and bias. This does actually exist. And the in count is the model, and the output dimensionality is 3 times the model. And we have input size, many values. Okay, so let's create our LN1 output activation. So that's this. And let's go back. And let's just print that result. So input size times the model should be in ln1 out. Okay, and let's really just check this. The input is going to be, yep, layer normalization out. Detention weight C tension out, yeah. This should be okay. Weight and bias. Input card, or count. Yeah, okay. Let's print. And we get 24.3, roughly. Let's just copy this here. And now let's check ln1 out. Yep. Retain the gradient and print the sum. And we get 24.27. Not exactly the same result, but I think this is close enough that we've done things correctly so far. All right. So now, basically the last step of our uh, attention block here is the layer normalization. And this should just be another call to our ln back function. And our input of this for the last layer should be the residual 2 of the layer before it. So layer 10 in this case. Yeah. Yep. I think this should be correct. Our weights are going to be ln1. DLD out is going to be ln1 out. Standard deviation and mean. DLD in is going to be res1 in 2. So we're just doing the same thing that we did for the second residual connection. Okay. Into. The weight gradient is going to be ln1. Same for this. And I think it does actually exist. Yep. Input con is going to be a demodel. All right. Actually, I think one thing that I just forgot is I want to check the weights and biases for the C attention matrix as well. So the C attention matrix is going to be demodel times 3 times demodel. And we're looking for gradients, H11 attention, C attention, weight. Let's print this. We get 296.98. And let's just print. Can delete this and delete this. Let's print this gradient as well for layer 11. And we get roughly the same value. Awesome. And the same for the bias, 2.53. the bias is 3 times d model. And again, we get roughly the same value. Awesome. Okay, now let's do the layer normalization. And this should be good to go. So let's first check the, let's say the weight matrix. So ln1 weight, which is going to be d model long. And we get 2.54. Okay, and let's print ln1 weight. Yep, pretty much the same value again. And now the bias 8.4. Bias has the same size. And we get roughly the same value again. Awesome. Okay, so the last thing we need to check if um, our input gradient is also the same. So activations back this, and this is input size times d model. And we have 1.06, and we're probably going to have the same issue that we had before, where we actually need to implement our residual connection as well if we want to compare it with the Python value. So let's do ln1 in retain grad. Yeah, and we have 3.6 roughly. So let's save this value and let's implement our residual connection. And we can just copy over this code. Okay. Where our input 1 is going to be res1 out, in 2 is going to be res1 in 2, and our output is going to be the previous layers res2 out. Okay. Size is still the same. And let's print those values. Previous layer res2 out. And we do seem to be getting a slightly different result here. So I think I saw one issue where our input gradient should actually be this layer's res1 input 2, because res1 out was set here. Okay, res1 out. Weights and biases should still be okay. So let's see if we get a different value now. Yes, and now we seem to be getting the correct value. Okay, so this was the last part of one layer. We've done all the gradient calculations that we need to do. And just like we did for the forward pass, let's now create a for loop over all the layers and propagate the gradient through all of these layers. So we're going to have a layer index, which will start at 11. And the layer index needs to be greater or equal to 0. And we reduce it with each loop iteration. Okay. Let's take all of this and indent it by 1. And at the very end, close. And think, let's just have a look if we don't have any constant 11s in here. But I think we should be good. Yep. All right. So let's make one last modification, which is that we don't want to write into 0 minus 1, of course. And the last residual connection is going to write into our embedding output. If you look again at our model architecture diagram, the first layer reads from the embedding output. So let's go to our activations back struct and create another one in here that's called embedding out. And it's going to be dsequence times dmodel. And now in the very last iteration, so down here, our layer index is equal to 0. We want to write to activations back embedding out. Okay, this should be, I think, the only change that we need to make. Let's just search for this. And we need to make the same change here, actually. So if layer I is equal to 0, our original input was activations embedding out. Otherwise, it's going to be the previous layer's second residual connection. Okay. And I think now we should be fine. So now let's just print the embedding out matrix to see if we get anything useful. So we want activations back, embedding out. Yep, I forgot underscore I. And we get 262.75. Let's copy this here. And I think we should be able to just check embedding out. So let's do retain grad and get the sum. And we actually get pretty much the same value. All right, awesome. So what we've now verified is that all of our layers correctly pass the gradients through the network. And now there's really just one small step left, which is forwarding our gradient to our WTE matrix and our WPE matrix. And if we think back to what we did to get the original values in the forward pass, is that we treated it as a matrix multiplication of our respective transform matrix, this one, or these two, times a vector that has one element set to 1 and all others set to 0. So if we do the backwards pass for that, it's only going to be this one vector in our transform matrices that are going to be influenced by our output gradients. And the amount by which they will be influenced is exactly equal to 1, because our input at that position is just 1. So I think that this final gradient calculation that we need to make is actually going to be very, very simple. So let's do size ti equal to 0 up to input size. And let's create the pointers that we need. So we have dl dout, which is just the output of our embedding gradient. Yep, this right here. Plus I times the model. Actually, is it? Yeah, yep. The vectors are the model dimensional. And let's create an end vector as well, or end pointer, plus the model. And let's create the two pointers to our WTE matrix gradient. So WT, let's do this. And this is going to be activations. Actually, no, this is going to be gradients. Gradients, WTE weight. And we're going to select the row of this matrix given by the input token that we use to extract that row. So it's input I times the model. And for our WPE matrix, DLWPE, we have float gradients, and we need to create our WPE gradient. Let's just move this one here and destruct WPE. And this one should just be the sequence times the model. If we look at our table, yep, the sequence times the model. So WPE weight plus our index of the element in the sequence, so just I times the model. And now we're going to have a very simple loop that loops from DLD out until DLD out end. Increment this, increment our token matrix, and actually this should be called DW, DLD WPE increment. And now we just want to take this value and add our DL out. And the same for the WPE. Okay, let's see if this. Okay, how do we check this is correct? Let's do the model times, or rather, the vocab times the model. And this is our gradients WTE weight at this index. And let's see if this compiles. Um, gradients WTE weight. Okay. And we get roughly 23,560. And let's see what we get in Python. So let's do WTE out. Actually, no, we want this gradient. Okay. And this one looks very different. Okay, so I definitely found one issue, which was at the very beginning of our backward pass, where we couldn't actually check the result for our WTE weight. And we seem to have forgotten to reset our in value. So let's do float in reset. And let's just set it to in. And down here, we'll set in back to in reset. And let's print this. And we get 922. And that's exactly the result we get in Python. Awesome. One matrix to go. So we have our WPE matrix, which should be the sequence times the model. and we get 262. Okay. And let's print WPE, and we get 262. All right. I think we have actually done it. Um, it's been 2 days. I don't have any idea how many hours this recording was in total, but quite a lot. Um, but in the end, we got there. We have all of the gradients with respect to all of our weight matrices, biases. Um, we have traced the output gradients back throughout the entire model, all the layers, and with these gradients, we could now do a training pass. So we would take these gradients, have some learning rate, multiply the gradients by our learning rate, and subtract that from the current model weights to get the new model weights. And this would be one training pass. And I think this is actually a thing I want to do in the next video, kind of implementing the LMW optimizer in C, for example. And yeah, with this, we've kind of laid all the foundation for that. Uh, Pretty crazy. We have roughly over 1,000 lines of code in total, spacing all the way back through our attention block, fully connected layers, residual, all of that. We have our loss calculation, which we checked, and then the entire forward pass. This feels like an eternity ago. Reading the weights and biases from the save tensors file. We've done that without using any kind of JSON library in C. We just did this by hand because we know the file format. We've done the encoding and decoding with a bit of help from Python, but we've kind of implemented our own encoding table in C. All of this was just one call to malloc. And yeah, this is kind of the final result of this very, very long video, very long 2 days for me. Um, but yeah, I I hope that this was kind of interesting in a way. Um, I gotta be honest, this turned out way longer than I could have ever expected. Um, but I think I'm just gonna go to sleep now. And I actually still have to edit this video. This is gonna be very interesting. Um, just cut out all the breaks. Again, this was 2 days. I ate, I went for walks. Like I just had like 2 regular days basically where I just coded almost the entire day. Okay, it's almost 12 at night, so I think it was a good 2 days. Thank you very much for watching, and see you next time. Goodbye.